So Ron Sauro was part of the development team for EASE, Electroacoustic Simulation for Engineers, which is a pretty cool software package, widely regarded as one of the most complete and accurate acoustics design simulation programs in the industry. It's really cool experience to hear something that has been put on paper and then turned into a thing, a reverberant space. You can hear all kinds of different flutter echoes if they're there, or reverbs or whatever, and that you had a part in that is pretty amazing. And I wanted to concentrate on that little bit because there's a whole bunch of things online that you can see about him. So without any further ado, Ron Sauro.
I keep reading. We have Zoom now. Okay, gotcha. All right. So for how many people were here 3 years ago when I did my last talk? Okay, well, okay. Because, and how many online, by the way, were here when I did the last talk? Any idea? Any hands?
I see one hand.
Uh-oh. Okay, well, all right, guys. Well, you just voted for an extra 25 minutes or so. So just want you to know that. In order to be able to understand what we're talking about now with the updates since 2023 to last time, I need to go back a little ways to be able to tell you how we got there, because it's all included in the whole thing. So the name of the last one I did was called Old Problems, New Solutions, Architectural Acoustics in Flux Redux. Just so you know, this presentation was done a year before that for ASA, and that's why it was Redux. And when I originally was asked to do this, again, I said it was going to be Redux. Well, I realized this is Redux. Okay, so it's updated 2023. So now we're going to go through the early part a little bit, which if you've heard it, I'm going to go through fairly fast. Okay, so that's me, president of NWAA Labs. By the way, somebody said that it's Northwest Audio and Acoustics Labs. No, it is not. It is NWAA, period. That's the actual name. NWAA used to be a consulting company that I had called Northwest Audio and Acoustics when I was consulting and designing systems and putting them in. But that's long gone, and I have to separate that from the laboratory. So, all right. For the people who don't know me and what I've done over the years, if you look on the right-hand side, you'll see a guy sitting in a chair. That's me in 1968. Okay. I was working at Ames Research Center in California, and my specialty was low field magnetics, and we were getting ready to launch Apollo and getting ready to launch the Voyagers, the Pioneers, and Vikings, all the rest of these things. And my specialty was low field magnetics and physics. And when DB Cooper got the first hijacking, we got a phone call a day later at NASA and said, how can you stop it from happening again? So, you know, being a magnetics guy, it was like, well, it's a gun. It has made out of steel. Therefore, we can get a magnetic field out of it. So what you see here, okay, there we go. Sorry about that. What you see here is a magnetic sensor that goes vertically this direction, and the other one goes down the other way, and they're added together, a comparator, and whatever the answer is, if you go through it, causes one side to go crazy, and you pick up a gun. What most people don't know is that in at least in those days, you could build a gun out of plastic or brass or something else and walk right through it, wouldn't even know it. I prove that every day I go, because every time I go flying, I have this wad of keys about this big, full out of brass, and I walk through them all the time. And then when I get to the other side, I go, it really pisses off the TSA. All right. Have any of you ever seen anything where we, at the laboratory, we talk about measuring speakers? And somebody says, well, that's an arc, and there's a lot of other guys that have done that the last couple of years or so. And I'm looking at them going, there's the first arc right there, 1968. It's magnetic sensors. And what we're measuring there is a radioisotope generator for the Pioneer 1011. These are the power sources for those satellites. Remember, they talk about Voyager being out there 20, millions, billions of miles away and still working. This is what powered it. Was a little nuclear power source. Now, why did we have to do it the way we're doing it here? Is because that little source is radioactive. It has no shielding of any kind, and it runs at 230 degrees centigrade. which will hurt you. So we had to figure out how to measure that. So because of this, I ended up having to design the ARC and the solid state multi-channel acquisition system. At that time, there were no acquisition systems. At that time, there were no integrated circuits, okay, or very few, RTL to be exact. So, and for the guys who are used to computers, they have memory, they have, hard drives. I'm sorry, when we did this, our storage was a cassette tape. That's what we talked about. Very, very slow. The whatever processor we had ran at about 10K hertz. Not gigahertz, not megahertz, 10,000 hertz. You can hear it running. One of the things I designed was multiple things for different things like Apollo, Viking. This is the lunar surface magnetometer that went on board all the Apollo missions. So that's my experiment. There it was, packed up, ready to go. And there it is spread out on the moon's surface. And we were measuring the moon's magnetic field at that time. And here is those two, remember I told you about those two RTGs we were looking at? There they are flying on this Pioneer 11, and that's my unit right there. Okay, so that was my specialty. It was doing light field magnetics for the Pioneers for Jupiter and Saturn. And then on the Voyager, that's my unit here, the same thing with the RTGs out here. I think it was, yeah, there they are right there. So these are the ones that went out past the end of the solar system. So this is what my background was, and 1968. So what you see there is the original thing I showed you earlier, okay? And here's what it evolved into at our laboratory. Okay, so now this laboratory is down in Elma. We test speakers and diffusers using this rig. So this little arc you saw before was about 1 meter. This is about 4.5 meters in radius. You can see how big it is compared to me, okay, because that's me down there. So what we're doing here is we're now working in a room. By the way, this is one of the largest free field opening rooms in the world. It will hold 4 football fields inside of it. Okay, this picture doesn't begin to do it justice. From our end here all the way to the other end is 690 feet. So that's a long way out there. This is 300 feet wide and it's 80 feet high. So when somebody says, can you measure in an anechoic chamber? Why? Anechoic chambers are supposed to simulate a free field. This is a free field. That's why we're able to measure all the way down to 20 hertz. There's our facilities again. That's our system for speakers there. This is for ceiling speakers and stuff like that. So I have a baffle. This is what we get out of a speaker. This is the directivity balloon out of a typical speaker. And this is frequency response at 19 microphones going from 0 to 90 degrees, all at the same axis. And so this is the kind of stuff that we report as far as speakers. This is our diffusion and scattering. What we're doing here is understand a speaker has a voice coil, you activated it, puts out sound, right? A diffuser is a speaker without a voice coil. So how do we activate it? We have a speaker behind here that goes down, hits this, and then the first order reflections are the diffuser. So now we can tell you what the diffuser does. So there's a good one. That's a barrel. You look at like a typical polished cylindrical. This is what it looks like. It throws out sound horizontally in all directions, but doesn't do vertically. There you go. That's from our data from our laboratory. What you see here is a simulation in the big balloon, and the one above it is the actual measurement. So all these diffusers you see, like quadratics and stuff like that, we're able to do this too, and be able to put it into simulation programs like AES to show you what it's going to do on a wall. So our reverb rooms, we have the largest ones in the world, 800 cubic meters. It's also the quietest. Our background noise is an average of around minus 20 decibels. I don't know if you understand what minus 20 is, but 0 is the threshold of hearing for a newborn baby. So we're 100 times to 1,000 times less, right? So you can actually walk inside this room. Okay, mine is 18, 20, average from 25 to 10K. And you can walk into this room. If you stop breathing long enough, okay, because by the breathing in this room, you increase the background noise by 25 dB, just by breathing. So if you hold your breath, hold it, you can actually hear the blood rushing through your ears. You can hear the blood going through your liver. You can hear your stomach turning over. It's very disconcerting to be inside here. It really is, because you feel your body's just kind of like having an out-of-body experience, or at least you wish you were. That's the kind of room we're in, and we are measuring at that point. So we use that as a background. So here is our transmission loss walls, 10 by 12. We're able to test wall structures like transmission loss all the way up to 74 dB or 74 TL transmission with no compensation all the way from 25 to 10K. Now, that doesn't sound like much, but in today's world, if you can get no compensation from 250 hertz down, that's impossible in most cases. Every compensation is whatever the last number was minus so many TL points, just to give you a number. Okay. So there's typical transmission loss thing again with windows. Here's curtain walls. Here's doors. This is absorption. We're going to talk about a lot about that. That's what today's talk is about, is mostly absorption. So this is a type A mount where you put something on the wall. Here we are with something is spaced off the wall. It's a E400 mount. Yes.
Ron, what's the Z in the KZ hertz? I didn't know if it was a typo on the first one, but it's on all of them.
Okay, let me go back. That's called not noticing. Okay. This particular slide is close to 3 years old. And I honestly had to put this all together about 3 days ago. So my own fault, sorry. Yeah, this is a mount that I invented for ASTM. This is for things like lapidaries and stuff like that. And this hangs up in stadiums and stuff like that to prevent the noise. So before they used to put it on the floor, and everybody said, well, it doesn't work like that in real life. Well, this is what it works like in real life. So we invented this and we made it a new mounting point. This is a new type of mount also. These are inflatable baffles for low frequency work. So remember all the little, if you go to gymnasium, you see all these little baffles hanging down that are made out of fiberglass that are flat about 2 foot by 4 foot. These are inflatable ones. So depending on how much you inflate them by, they will have different low frequency absorption. And that is the biggest thing, by the way, in the last 10 years now, low frequency has become a very important thing because low frequencies really cause problems with people. So anybody ever hear stories about the windmills and problems with, I think Trump said something, yeah, you get cancer from having these things running around. Okay. You don't get cancer, but you do get other things. People don't know this, and people are finding this out now. The low frequency, what we call infrasonics, is generated by the windmills, and it goes down the stub of the ground with the stand that holds the windmill up, goes into the ground about 60 to 80 feet, and then transmits through the rock into people's homes and causes the walls to vibrate at somewhere around 20 hertz. Low frequency, anybody ever hear of an organization called SMPTE? SMPTE, AES, people should know this. Yeah, Society of Motion Picture People. Okay, 1932, SMPTE did a study about low level infrasonics. How many of you ever watched old horror movies? Frankenstein, all the stuff with Lon Chaney and stuff. Did you ever notice before anything happens that makes you nervous, you'll hear a little rumble in the background, like, okay? That low frequency makes you tense. It makes you upset. It causes flight and fight things in your hormones in your body. Okay, that causes the adrenaline to go crazy. Okay, I hate to tell you, but that adrenaline going crazy tires you out and makes you stressed out. This is what happens with the windmills. It causes your house, when you live in this house, you have sleeping, you have all this stuff going through your body and you hear it all the time and it makes you stressed out. And
Ron?
that causes things.
Ron, when you're talking about windows, are you talking about the embassies that we're having?
Windmills,
Okay,
wind turbines, thank you. Okay, by the way, I'm 77 years old and I reserve the right to forget words once in a while, okay? So, but in essence, what this is intended to do is absorb somewhere between 30 and 100 hertz, which very few things do. So I just want to give you a heads up. We get into our research now. This is what we did the last time, 3 years ago. Okay, we found out, this is, by the way, how we test absorption materials. How many of you ever put absorption materials in rooms to absorb sound and you just put it on the walls and make a big band of it all the way around? Very common, right? How about if I told you put in about 3 times too much? Okay, this is what we always assumed. Absorption material was always dependent upon the area. Okay, that's what we're going to talk about today. It doesn't. In fact, area is only about 1/3 of the absorption. The rest of it has to do with configuration. So that's what we're going to talk about. Here we measured a solid piece of absorption right here. Okay. We also took that same square area and we separated it like this. It's the same amount of square area. Okay. There we go. Okay. Let me go back. Just be aware of what we just talked about. This was not continuous. Okay. One of the things we're going to talk about is a T-type mount, which is a proposed type mount. Why is this important? How many of you put chipboard in your rooms when you try to simulate them? It's what they're built out. These rooms are built out of chipboard, right? How many of you think that the typical thing that's out there, absorption, says that we have a low frequency absorption on chipboard, 1/2 inch and 5/8, that around 125 hertz, it just sucks up the sound because it diaphragms like a drum head does. Okay, how many any of you do that? Okay, well, that has been the known process for 50 years now, 60 years. That's what it's supposed to look like. If you look at the red one, that's what everybody has been reporting for the last 50 to 100 years for chipboard, that absorption. You notice it has a lot of it at 50 to 63. This is because it was tested incorrectly. You put it on the floor flat, and the floor is a concrete floor. One side of it is against the floor, and the other side's up. Okay, the sound hits the front face, goes through the front face, hits the back face, and because it's hard and doesn't diaphragm, it reflects back up through the front face and back out of the room. And that's why you see the absorption. Now, if you take that same wall and you put it, I'm sorry, I'll go back one more time. You put it in that window, it goes through that through that wall and through the next wall into the next room and disappears. It doesn't reflect. So if you look at the blue, that is the actual absorption. If you're looking at a room or a wall built inside of a building. Now, if you have an outside wall that's built on the outside of the house and it has a solid wall on the outside, then it will do what the red says. So it's 2 different measurements you have to have in order to be able to configure and figure out what the reverb time of your rooms are. Okay, so here you are with 1 layer on each side of the wall, 5/8. Here you are with 2 layers, 5/8. Be aware that when you're doing this, if you're doing it in a room that is built like a studio or something, you need to accept the fact that there is no absorption that is effective from these walls. It doesn't happen. Okay, it's going to reflect everything. Okay, so be aware of that if you're doing modeling, you need to reduce that official one you buy that you get in the programs for absorption and take it from the low frequency and take it down to 0. Otherwise, you're going to overestimate the low frequency absorption and you're going to have a problem with intelligibility in the room. Okay. Is the area enough? This is what we just talked about. Is the area enough? Okay. Let's talk a little bit for the people who have not been here before. What is sound absorption? Anybody ideas? Okay,
Kinetic energy gets absorbed by the.
how?
The answer is right.
Talk in the mic, please.
Yeah. What is it? It's the conversion of acoustic energy to thermal energy. By the way, absorption is this period. No matter what you do, whether it's acoustic energy or radar or light or anything else, okay? It's a conversion of energy to thermal energy, okay? You lose it in heat. What is the absorption coefficient? This is what we use in all of our work. It's the result of dividing the absorption by the sampled area. Now, that word, coefficient, the coefficient is a mathematical construct that is determined to tell you that whatever occurs will occur between 0 and 1, 1 being perfect, 0 being nothing. Okay, that's a mathematical construct. They tell you that absorption coefficients cannot exceed 1. Well, as long as you call it a coefficient, that's true. But if you call it an absorption constant, then it's any number. Now, if you take the amount of absorption and divide it by the area, and you get an answer of 1.7, I'm sorry, that is the constant. Because in order to rotate it back the other way, you have to multiply it by 1.7 to get back where you started. Otherwise, you underestimate the amount of absorption in a room. Okay, so this is a problem we've had since 1927. Okay, how many are familiar with the name Sabin? Anybody familiar with that name? Okay, how many of you are aware that there were 2 Sabins? Anybody? Okay, Wallace Sabin is the guy who discovered absorption. Okay, everybody knows that story. He went into a room and had an organ pipe, and he hanged it and stuff, and then he put stuff in the room and said, oh, reduce. How much it reduced basically was the energy. They called it the Sabin. So if you have absorption, it's called a Sabin. Okay, but anybody familiar with the name Paul Sabin? Paul Sabin was his nephew, who was the next generation. Anybody familiar with a place called Riverbank Lab? That's the testing, that's the oldest testing laboratory in the United States in Chicago. It was founded by Paul Sabin in 1915. Okay, it's everything is based upon that laboratory. Anything you see, all the measurements in the last 50 years come out of Riverbank. Okay. He proposed a coefficient in 1927 at the ASA meeting. And I will have to tell you, I've been a member of ASA for a very long time. And today we are a fellowship of people who are very polite. We never call our fellows, idiots or whatever. There's a lot of different names you can call people. Okay. But the point is, we don't do that. We're polite. 1927, I found out that they were not quite so polite, because I read the proceedings of the 1927 ASA meeting, which was the first one, and Paul Sabin presented a paper on converting absorption into an absorption coefficient so that we could use it as calculation. And there was another guy named Chrisley, who was also a big guy in the industry, and he was in the paper right after that. And when he got up on stage, he basically said, and it's written down on the paper, Paul Sabin is an idiot. That was right on stage in front of everybody. And why was that? Because he tried to create this coefficient instead of a constant. That argument has now been going on since 1927, and we're still doing it. I belong to the ASTM C423 committee that writes this stuff, and we still use the idea of a coefficient. Why? Because nobody wants to change it, because there's a lot of people out there that have been doing it this way for 60 or 70 years, 100 years, okay? ASTM C423 and ISO 354, 2 different groups. They require similar shaped samples. And 17497, anybody hear of the term scattering at all? This is a random scattering of anything that's in a room. How can I describe this? How many think that the cathedrals in Europe are great sounding places? Everybody talks about the acoustics of these big halls, these opera halls and stuff. And supposedly it's because of all the statues and all the stuff on the walls, you know, scattering the sound and making the reverberant sound more pleasant. Okay. That was supposed to measure scattering in ISO. I can tell you from having been the only facility in the world that could actually measure full scale, it doesn't exist. Okay. It's a mistake, big mistake. We're still in the process of trying to get rid of it because of it. Because what happens is you're going to find out that that particular function that you see there was put into these calculation programs to compensate for the fact the absorption wasn't correct. And when we actually do the absorption correctly, you don't need it anymore. It actually takes the place of it. So what we call scattering is actually a part of absorption. Okay, so we're going to use these different methods of measuring the RT of a room, impulse response and or interrupted noise, et cetera, different areas, different perimeters, et cetera. And you notice at the very bottom, all these standards provide different answers for how much sound absorption. Now, if you're putting your reputation on the line as a designer, and you're telling a customer, I'm going to put a speaker system in your room and it's going to do this. How many of you know that the direct to reverberant ratio determines how intelligible it is? You have to have a certain amount of direct sound, like we have in here. We have a lot of great direct sound in this room. You hear speakers. Okay, the room is fairly well treated. If you go into a room that has a lot of reverberation, you have a problem with being understood. Later on, I'm going to show you what a reverb room sounds like. You actually can hear it. It has 8 seconds of reverb. And take my word for it, when you talk to somebody and you're only a foot away from them, you can't understand them. And if you turn your head, you definitely can't understand them. That shows how effective direct to reverberant ratio is. So we're going to talk about why we have different answers for absorption coefficients. So we're going to recommend sampling the materials 2 different ways. We're going to measure them. We're going to look at the perimeter lengths, look how the shape is, et cetera. And we're going to calculate those things. So if it's not area, what else? Okay, first experiment, we did a circle. Okay, this, by the way, anybody familiar with something called Owens Corning 706? That yellow board fiberglass you see all the time and putting on the walls and stuff. Okay, this is the most popular material to use anywhere. So we had a circle, we had a square with exactly the same area. We had a rectangle with exactly the same area. We had a long rectangle with exactly the same area. And we divided it up on the floor in sections of 2 foot by 2 foot with exactly the same area. So by rights, if this is correct, these should all have the same absorption coefficients because it's the same area divided by the amount of absorption. Okay. We also, by the way, did the same thing going the other way where we kept the same perimeter and reduced the area. So you can see the areas disappeared quite dramatically. In any case, I hate this. Okay, it looks like I jumped here a little bit. Yeah, let me go back and we'll go back through that. Okay, this is okay. There we go. That's what I wanted to show you. Okay, so what you see here is the absorption coefficient of the circle up here, going all the way out to the broken part. Okay, so this is, remember we talked about coefficients. They're supposed to be the same. It's the same area divided in the amount of absorption. You should not see the difference. It should be the same thing over and over. So what this is saying is we have a lot more absorption out of those little pieces than we do out of that big 10 foot by 12 foot piece. Okay, and you can see it right here. These are actual absorption coefficients. And we tried the same thing with the perimeter to be sure whether the perimeter did the same thing. And what we have is this, does the same thing. And how do we know it's accurate? Anybody know what a regression is? An R-squared regression? If you take the data from multiple experiments and plot them basically upon a linear scale, then we should be able to look at it. And the more linear it is, the more the data is realistic. Okay, typical R-squared for agreement is around 0.7 or 0.8. Okay, if you look up here, yeah, okay, you'll see that our area versus perimeter, absorption versus perimeter, comes up with a coefficient from 160 hertz all the way to 8K, 10K, of 0.999 in a lot of cases. This is virtual certainty. Okay, this indicates that everything we're measuring is very solid. Anybody who know a person called Leo Baranek? Anybody that know that name? Okay, he just died a couple of years ago. He was 100 and some odd years old. He is kind of the grandfather of our industry. He's the one that described everything in our industry. And I got a chance to meet him in my first presentation. And I was giving my presentation at ASA at Doral, Miami, 2000. And I finished my presentation, and all these people were kind of going like this, you know, it's like you're complaining about Saban and all the rest of the stuff. And this guy walked up the aisle to me, and I didn't know who he was. I had no idea who he was. And he was standing there. Now, remember, this is Doral Country Club in Miami, or in Florida. He walked up, he was wearing lime green pants, a lime green jacket with a yellow shirt and a lime green tie. And you have to know Leo. He's short, he walks with a cane, and he has, at that time, he was probably about 90, 97, 98 years old. And everybody, you know, personally, I read his books. I never met the guy, didn't even know he was around. And he walked up to me, he says, Mr. Sauro, he said, I want to introduce myself. He said, I'm Leo Baranek. And you know, my mouth must have dropped down to my chest somewhere in that area. And he has this very, very intense sense of humor. And he said, and I'm not dead. He said, I listened to your presentation. He said, I was ready to argue with you on every single thing you came up, you decided on. He said, I didn't think you were right. He says, I just knew it until you showed me this particular chart. He said, I saw that chart, and he says, I only have two conclusions. One, you drew the lines first and then put the dots on them, basically saying you cheated. Or he said, you actually figured out what edge effect really means and actually figured out how to make it work. And he says, and for that, I congratulate you. And he says, I think I'm going to give you the benefit of the doubt. I think you probably figured it out. Like I said, he was a very, very great guy. To me, that was the biggest compliment I ever got in my life. Okay. But this chart has been the source behind that. Let me go back a little ways here now, because I screwed up. Can I say, hey, we all make mistakes. Okay, so how many are familiar with the types of absorption there are? Okay, if you have fiberglass, like pink stuff in the walls or FR 706 or anything like that, it's what we call fibrous. It's made with strands of material and it's glued together, and the air and the sound goes into it, and because it goes through, it has to weave its way through all these things. In doing so, it slows down the velocity of the particle. Okay, when you slow it down, the energy has to go somewhere, and it becomes heat. Okay, so that's how it works. It's called flow resistance. You resist the flow, you convert the energy of the sound into heat, therefore absorption. Okay, now we're talking physics now. Okay, you have diaphragmatic resistance. Okay, what does that mean? Any of you play drums? Okay, good. If you hit a drum head, it does this, right? This action is not what's causing the problem. It's the flexing at the edges. How many of you have ever taken a piece of metal or something and done this? And when it goes through that change, it weakens, it gets hot, right? That hot is the heat, it's losing energy. Okay. So where you're losing the energy is around the rim, where it's attached to the rim, and this thing is moving in and out, and it's flexing this edge over and over again. That's how a drum works. Okay. So it loses energy by flexing. So that's called diaphragmatic resonance. There's also air resistance. Familiar with shock absorber in a car? Okay. You have a sealed area with a piston and you shove it really fast. What happens? If you push it really hard, it gets harder and harder. That's how it absorbs energy, right? Like a shock absorber. And in this case, they put liquid in to help it even more so, but you can do the same thing with air. Okay. Ever played I'm trying to remember what they call it. It was like a flute, where tin whistle, where you have that little thing moving and changing frequency. That's what it's doing. It's changing the resistance of the air inside. Pipe organ, perfect example. You get the air going in a pipe, it goes back and forth, and every time it compresses, it loses energy, and every time it decompresses and goes the other direction, it basically gives up and continues on losing till it finally decays away. That's air resistance. That's been the only method of absorption that we are aware of for the last 100 and some odd years. Okay, when we start talking about this edge effect, what we have is this. Okay, I hate this. There we go. Okay, we know from research done by Birdside at Ohio State University about radar. What you're looking at right here is an incident wave coming in. It hits a sharp edge and it bends, diffracted. Okay, what we know is that anytime you bend anything, you change the phase. And when you change the phase, you lose energy. So when we bend the sound like this, we lose energy. And how do we know this? It's sound you can't measure. It's so tiny that it's infinitesimally small and you can't measure it. But we know in radar, it acts the same way, just a shorter wavelength, the same kind of energy. And how do we know this? Because in this case, we were using a 35 megawatt radar. And you could actually measure the heat loss because that edge right here got red hot. And somebody said, oh, well, it's got to be the metal because it's made of metal. It heated up the metal. Okay, so we took that out and put a piece of wood in place of it, and the edge burned. Then we put a piece of fiberglass in and it melted. Okay, well, we aren't affecting the material evidently. So what we figured out was we were heating the air right here at that point in the air, and it got so hot that it actually melted the edges, okay, with the radar. In sound, we don't get that hot. You don't need to measure it, but it loses energy, okay? So if you look at the edge of an absorber, this is what you have, okay? Energy comes in from random directions, okay? When it hits an edge, doesn't matter, just an edge, okay? It will always come off normal to the edge. Normal, if you're not familiar with that term, 90 degrees, perpendicular to the edge. So there's the edge of the piece of material. And you notice on the arrows, they all come out the same direction. Okay, what is it? What just happened? Well, number one, we changed the direction of the sound coming in, and it's all going out the same way. Okay, that was a loss of energy right off the top. But what else did it do? Everything is now going in the same direction, the same air and stuff like this, and it becomes what we call coherent energy. This means it's all the same phase, the same direction, the same everything. And what is the best example of coherent energy out there? A laser. Have you ever noticed that if you take a laser beam and you hit it, it's a dot here and it's a dot way out there? Okay. If you have a flashlight and do the same thing, it disperses. That's because it's incoherent, different phases. In a laser, it goes like that. And you can shoot that laser beam all the way to the moon. It'll still be the same size. Now, how do I know that? Because remember I told you I had something on the moon? We have reflectors on the moon. And we the little square thing. It's about 2 foot by 2 foot. It sits right on the moon. And we actually shoot a reflector or a laser beam at it once a month to tell you how far it is exactly from here to there and back again. So we can measure it within 3 inches. Okay. And we've done that since 1968, 69. Okay. That was one of the first experiments. This is why when you have people telling us that we didn't really land on the moon, well, how can we bounce laser light off of it and come back? Because we have a mirror up there. We know exactly where it's at. You know, so this is the first thing is we have coherent energy. Now let's take that edge and convert it to a plane by moving it downward. So you have a thickness like that. Now the energy comes in, it comes off perpendicular to it, but it also moves downward 45 degrees. And why is that? Because if you have a downward angle of 90 degrees the incident angle will be half of that. That again, pure physics. It's all light theory. So all this energy is going to come off of that thing, and it's going to increase the absorbency. You've now changed one direction, okay, coming in from the random direction, going out, and then you're changing it again, going downward. This is a double shot. This is why the edges add absorbency to the material. Okay. Why does a circular sample have less absorption than a square? I can show you the data on that, but the circular, remember we talked about the first one was a circular sample? It has the lowest amount of absorption of all these shapes. The shape has a big difference. Why does it happen? Because when the sound comes in and it's this edge, it comes off normal. If you come off of the circle, at no point does the sound go the same direction, because it's always changing shape as you go around the circle. Therefore, all the energy coming off is incoherent and it doesn't add. Okay, that's why a circle has 20% less absorption than a square of the same area. So this is why it gets really crazy. So is area enough? Based on the results, leave the area-based coefficient alone is not adequate, et cetera. Is it more important than expected? Yeah, okay. The facts are we can almost double the absorption by taking into account edge effect. So there is a formula that we came up based upon just the edge effect only. Now it looks really complicated, okay, but it looks really scary because anybody who can do multiplication and division can do this. You don't have to have a degree in our algebra to do this. That's one of the things that that Leo said when he looked at it. He says, I looked at that formula and first thing I looked at is, it's math. It's not even algebra. He says, what I've discovered is when people present papers and they have this really complicated mathematical stuff, he said, the more complicated it is, the more bullshit it is. Leo, by the way, is very plain spoken. He said, yeah, he said, the simpler the formula is, the more likely it is to be real physics. He thought this was fairly simple. So if you take it and you reduce it, you can take all those terms you saw earlier, all these terms you see up in here. Yeah, like, okay, do that one more time. All these terms up here inside of this set of parentheses can be reduced to a single term. Okay, so something we call KAB, the constant of absorption at each frequency. So you take that, now you can reduce that formula to look like that. Much simpler to look at. And it's easier to understand. There's a gentleman in our industry who has been kind of my nemesis for the last 10 years because he worked for Armstrong Corporation. And what we've learned is this. In things like ASTM, when you represent a company, you cannot represent necessarily what you know in science, but you have to represent what the company says you're going to do because it's in their financial interest to do this. When you retire, then you can tell them to go do something to themselves and you can start to actually be a real scientist again. Okay, take my word for it. This is part of science. This is part of everything out there. ASTM is a standards committee. Now, I always thought when I got into it that we're all trying to search for the truth. Okay, I will tell you this. What I've learned in 15 years of being in there is we're not interested in the truth. We're interested in what everybody agrees on is an answer. And as long as we can all get the same answer, whether it's right or wrong, they're happy. Okay? It's one of the dark secrets of our industry. This is the frequencies that we have here. I did what they call an interlaboratory study between all the laboratories in the United States and in the world. So we sent a sample out to everybody, had everybody measure it, and we gave them separate things to measure and come up with answers and send them back to us so we could correlate them all and see how accurate our industry is. Okay, so if you have a 6x6 sample, that's the red line. Actually, yeah, right. There's an 8x8, which is the green line, 10x10, which is the purple line, and 12x12, which is the light blue line. Okay, Forget the one on top because that's the separated 2x2s, and we're going to eventually drop those right now. Okay, but that's what you see here. So here we are coming up with all these laboratories saying that if you, depending on the size sample you can have different absorption coefficients. Now, how are you supposed to use on a wall when you have no idea which one they're using? Come up with those numbers. These numbers can vary as much as 50%, 60%. So how do you use this stuff? You can't. That's why we're doing what we're doing. So here we are. These are calculated based upon what we measured. Okay, this is the same chart, just spread out. Okay. Bob, by the way, Bob is a guy named Bob Hallman. He was the head of engineering and science for Armstrong. He came up with an idea. In my system weights, you had to measure two different things. You had to measure in a monolithic piece, and you had to separate them. That means two tests. This means it's twice as expensive to test as it is to do the normal test. It takes two tests to do it. You got to charge it for them somehow. So he was trying to figure out a way of calculating it mathematically. So we came up with the same answer, no matter what the shape of it was, no matter what the size was or anything else. And he made a proposal for it. So he defined a virtual area that says it's a footprint plus a wavelength related area associated with a perimeter. So you have a certain length perimeter, you go out from that perimeter, and that area is an increased footprint of that space. Instead of a 2x2, it may think it's a 4x4 depending on the wavelength. Okay, so he came up with mathematics to do this. And he basically figured it out. So this is what we ended up with. Here's what we had. We measured the ILS. You can see these same numbers again. Okay, we're going to leave out that big peaky one. So he did his own thing, and this is what he came up with just the separation of the panels. Okay, we predict what an 8x9 will be from a 10x10 or a 12x12. So what you see here is these predictions using just the alpha, just the normal absorption coefficient. This is what the predictions would be of the absorption for these separate things, which is close to what we measured. Okay. After doing all of our work on it with using perimeters and calculating using perimeters, this is what we came up with. Okay. So now we can predict fairly accurately, no matter how big the sample is, what the absorption coefficient is. And that's how much closer it is together now, or at least it was when we started this process. So now we can do a different thing. If you use a low absorption material like these tiles, like here, these are called mineral fiber tiles, and they're very low absorption in comparison to carpet. Then we have this problem where you can see the separations, okay? And that's because if you use just the perimeter only, there's not enough information there because of the wavelength. So now we're going to predict what we have with this variable effectiveness, this perimeter that appears outside. It covers the empty areas. And you can see how much closer we are. Here we are with variable effectiveness, et cetera. So the idea here is how do we predict this stuff? And before you saw those other numbers that varied as much as that much, and you can see how much closer we are now using this new formula. We're going to go over that formula in a few minutes here. So ISO has a group called the Absorption 354, and this is one of their guys' proposals to do it. And you can see the differences in their proposals. Okay, so here's using the ISO method, et cetera, and you can see the differences. And by the way, you have to be able to know both of them. You have C423, which is ASTM, and ISO 354, which is the world, the rest of the world. And this is what we get. So now if we use Bob's method, this is the deviations, okay, I'm sorry. So this is deviations here between the predictions from the alpha to what we have now, or the original alpha, the original absorption coefficient. These are the deviations with our system, much lower deviations. So predicted absorption. You now have a comparison here. If you look at the bright red line, that is my information based upon a measurement of two different materials. Takes twice as long, costs twice as much. And you can see that Bob's predictions and all the other things are very, very close to what I actually measured. Okay, so this shows that the method we're developing is a usable method to predict what the absorption of a room is. Okay, Now, here we are with mineral fiber. How accurate is it? Same thing. So we're going to go into this a little bit now. And one of the other things we found out is this. If you separate materials from a monolith and you start separating it into pieces like this, it increases the absorption as well. And that's not because the edges are exposed, because if you notice, the edges are covered with steel. So we're only looking at the surface here. So look, we're looking at a 6-inch spacing, monolithic. We're looking at a 12-inch spacing. We're talking about an 18-inch spacing. And now we're talking about a 24-inch spacing. Okay. There's the absorption coefficients of the spacing, same material. Now be aware that we've already taken into account by this time the edge effect. So this is additional absorption that you get just from spacing them apart. And you can see it goes all the way from 1 average all the way up to 1.6. Now, the one thing you do notice is if you look at the gold one at the top and the light blue or light greenish one, that they're virtually on top of each other. One is 18-inch, one is 24-inch. What does this say? It says if you have a 2-foot by 2-foot unit and you space it by up to 2 feet apart in all directions, at some point between 18 and 24 inches, there's no more increase. So it only covers, and what it comes down to is we've done this with 4-foot pieces. At 4 foot, same thing happens. So whatever size sample you have, the space between it and the next sample can be the same as the sample is. So if you have a 2-foot space or a 2-foot material, you have a 2-foot space and 2-foot material. And that 2-foot space in between has just as much absorption as the material itself does. So I think somebody said that they did a whole wall of these things. Well, if you've taken it and divided it up into 2-foot by 2-foot sections and then put 2-foot spaces between them, you would have had twice as much absorption with half as much material. Scary, isn't it? Cost half as much money too. Oh, by the way, this is the reason I'm doing this is because also in the standards and also in our understanding of our industry, they always tell you, you have to keep everything aligned. If you have a square, the next one has to be aligned with it. It has to be parallel to it. It can't be rotated. It can't be various shapes and stuff, okay? Because that causes problems because they interfere. They don't work together, okay? So here we have 24-inch aligned on one side, and I have 24-inch unaligned, just scattered willy-nilly. They're all 24 inches apart, but they're just different shapes, okay? Supposedly, the one on the right has less absorption than the one on the left because they're not aligned. There's the answer right there. That's 2 different measurements, light on top of each other. 24-inch aligned and unaligned. They're identical. Okay, that puts to lie this whole idea about, things do this. By the way, there's a lot of myths in our industry, a lot of. In fact, the majority of our industry is mythical. Okay, that's because people had these ideas in their minds about how things work, and they ran with them. It was like, well, if this happens, this must happen. No, that's a simple answer. No. Okay, it must happen. It probably will not happen. Okay, I always tell people, science doesn't care what you believe. Okay, it is what it is, whether you like it or not. And it will do what it's going to do, whether you like it or not. And most of the time, it will do what you don't think it's going to. Okay, so here you are in that first thing. So we did the same thing with 18-inch because we figured it's going to get closer together. Oh, there's the answer. And then we did the same thing with 12-inch, and there's the answer again. And we effectively did this over and over. So now we had to take into account not only the perimeter of what it is we have, but also how far apart these pieces are. So now we have a new formula. Here's our formula right here. Calculate the area based upon the edges. You do this, etc. Okay, anybody familiar with calculus? Okay, you know what that little signal is right there? Yeah, integration, right? Okay, so all we're saying is take all the pieces, add them together, distance the edges, and then we added this little thing here 2 days ago. Now, I'm going to show you how up to date you are in this situation, okay? This formula has only been around 2 days. Okay, so you guys are the first to see it. Okay, this was just sent to me by email this morning. So if you want to talk about being up to date with the latest research, you're the first group in the world to see this. I mean it. It hasn't been released yet. So this formula right here is the formula for calculating spaced objects with the perimeter taken into account, if you want to calculate absorption. So just keep this in mind. All you have to do is have the original measure, or the original measurement they give you in the books all the time, take it, run it through this formula, and now you will know exactly what the absorption of that material is, no matter how big it is, how it's set up, or how it's distributed. Okay, so if you want to, at some point copy this, etc., you can get all this information here, but this is the latest algorithm here. Okay. This is the formula that we had a month and a half ago. Okay, the actual measurement is the gray one up here. And these were different things, trying to figure out how to calculate how far apart things are, what the wavelengths are, how they affect each other. Everybody familiar with what we call dead horse? Absorption has been a dead horse for 100 years. Okay. Anybody familiar with a group called NIST? The National Institute. Okay. These are the people in the United States government who tell us what is the standard. Okay. We called them up because they have standards for acoustics and asked them to talk to their standards people. And a guy, a nuclear scientist, answered the phone. And I said, can I please talk to somebody in the acoustic division? And he says, well, that division doesn't exist anymore. This is our science government, okay? It doesn't exist anymore. What do you mean it doesn't exist anymore? Oh, well, we've discovered everything has to do with science, so there's nothing more to discover. So they disbanded it and tore down the largest anechoic chamber in the world because we no longer had need for it, because the basic science has already been done. And I'm telling you right now, what you just saw is what we call basic science. We're discovering new things constantly. And yet we're being told it's mature. There's nothing more to discover. So as you can see here, it's our job to beat this dead horse. Okay, that's what our job is. Everybody in here is supposed to beat this dead horse. Now, why am I saying that? Because this is something that the majority of you out there believe. I have to fight this daily on Facebook and other groups because people come to me and say, absorption, 0.9 absorption is 90% efficient, okay? And at 1.0 is a full coefficient. That's 100% absorption. And I'm looking at them going, okay, so if I put a material 0.999 absorption in a room, how much sound is remnant? Oh, well, it absorbs 100% of the sound. I says, how do you know that? And they go, what do you mean, how do I know it? I can hear it. If you can hear it, it's not 100% of the sound. 100% of the sound is all the sound, okay? This means all the sound in the room will disappear and you will be in a vacuum, okay? But you know that's not happening because you put it on a wall and say, I got 100%, I got 1.0 on that wall and it reduced the sound. And I'm going, yeah, it reduced the sound, but it's not 100%. And they go, well, that means that. I said, no, it doesn't. What it means is a coefficient. It has nothing to do with the amount of sound or anything. It is just a number. It doesn't have any units. It doesn't have any dimensions. It doesn't have anything. It's just a number as a constant used in mathematics. How much work does it really do? Well, I'll give you an idea. 0.9 absorption coefficient absorbs about 6 dB of sound. That's it, 6 dB. 0.99 absorbs 8 dB of sound. And 0.999, which is a lot of absorption, absorbs about 10 dB. What does that mean? If you put a 6 inches of fiberglass on a balcony face and you shoot sound towards it, you're going to get sound back. I don't care how thick that stuff is. Okay. That means that that balcony face just absorbed 10 dB of sound. Now, if you hit it with 100 dB, you're going to get an echo back at your face of 90 dB. What do you think? You've made that balcony disappear or that rear wall disappear? No. Okay. The only way you can stop it from getting back to your face is not to absorb it, but to redirect it away from you. That's what diffusion is used for. Okay. So again, I will say this. It's not 90%. I want to make sure that this gets back to everybody one more time. Stop being a dead horse. We're getting too many air bubbles. Okay. I'll say it one more time. Coefficient is not a percentage. Okay. If you don't remember anything else about our talk today, it is not a percentage. Okay. Settled branch of physics. We just talked about that. We can measure absorption. No, we cannot measure absorption. We have no idea how to measure absorption. What we can do is do what Wallace Sabin said, and as we can measure the results of the absorption. So the way you find out is you have a room that has no absorption in it at all, and you measure the reverb time. And then you put absorption in the room, and you measure the reverb time again, and you subtract them, and the difference is the absorption. Okay. Now, that doesn't mean you can go into your bedroom or your recording studio and put something in the room and measure it and say, this is how effective it is, because you don't know what else is in the room and what's affecting the sound. The only way you can find out is to have that material put into a laboratory setting where we have a room that has virtually no absorption. It's called a reverb room. It's made with concrete walls, concrete ceiling, concrete floor. It echoes forever. Okay. Our reverb room is the largest in the world, and it has around an 8-second reverb time of audible sound. Now, the RT60 is really 35 seconds. Okay. To drop it down 60 dB, it takes 35 seconds for the sound to go away at 125 hertz. Now, you know, can you imagine what it sounds like? We'll show you later on. Okay. But we can't measure it absorption directly. Baffles. I love this. Baffles hanging in the room. 2 sides, right? Has twice as much absorption. That's what they say. In reality, it's only what, 1.2 to 1.3 times. And why is that? If you put baffle on the floor, sound goes in, hits the floor, or goes through it, hits the floor, and bounces back through it. Goes through the material twice. Once going in, once going out. Okay, that's how you measure it. If you hang it, the sound goes through it and continues. It never comes back again, unless you have to take into account the sound coming in from the other side, going through the other direction. That's why when you start averaging it together, it only is about 1.2, 1.3. So you can't make the assumption that because there's 2 sides, it's double the absorption. It doesn't work that way. I have people all the time coming to me saying, I'm going to hang baffles. And I've heard that if you hang them in a herringbone pattern instead of a straight parallel pattern or a box pattern, it's more effective because the sound bounces back and forth between these different things. And each one picks up things in a different pattern, et cetera, and stuff like that, because it bounces from place to place. Okay, I can tell you, we've measured them all over and over and over and over again. There is no difference of any kind. All that's happening is the absorption is in the room. It doesn't care what position it's in, what shape it's in, or anything. It doesn't know it. It's just a piece of crap sitting in the room as far as it's concerned. Okay, so I'm being as honest as I can. It has no effect. How many have heard the thing about taking a baffle and taking it off the wall about, 6 years? Well, say you have a 3-inch baffle. Let's take it off the wall 3 inches. That will increase the low frequency absorption. Okay, that's a very common myth in our industry. Okay. We've measured these things till we're blue in the face. The best, now there's two ways of doing this. One is to take it off and put a spacer behind it, and then you have an empty space behind it, right? It's the easiest thing to do. The maximum you can raise these things off the surface is 1 inch. That's it. Anything over 1 inch, there is no more absorption increase. Why is that? Anybody familiar with the term fluid dynamics? How fluids move. Okay, well, let me tell you something. Fluids move the same as sound moves. How can you tell this? How can you tell you have a good absorber? If you take a piece of fiberglass and you take water and throw it at it, what happens to the water? Sponge. It's absorptive. Okay. If you take a piece of plastic and put it on top of that fiberglass and you throw water at it, what happens to it? It bounces off, right? That's because it's reflective. It's a hard surface. Works just like sound. Funny how that works. Okay. An example. Anybody familiar with what they call a reverberant field in a room? You stand out in the room, right? You can hear the sound. How many guys have you ever heard to take a little sound meter, like a Radio Shack or something, or even an expensive one, and they put a sound system in a room, and they go, here, put pink noise on it, and you can walk it around the room, and when you get to the back of the room or 3/4 of the way back, it'll be the same level no matter where you go. Okay? That's called reverberant field. Okay, and then if you're in the front, it gets louder as you get closer to the speaker. At some point, you're going to go past what we call critical distance, where you can no longer hear the speaker, but you hear the room only. That's it. How can you explain that to the average person? Well, we have a bathtub. Okay, I'm going to give you a bathtub with a 2-inch drain. I'm sorry, a 1-inch drain. A 1-inch drain. It has a faucet that has a 2-inch input. So twice as much water is going into it as going out of it. So at what point does the bathtub fill up with water, or does it? Any answers? Think about it. We're going to put a lot of water in this tub, and it's going to have an open drain. Does the bathtub fill up? Twice as much going into it. No answers? Nobody wants to look foolish? Okay, the answer is it will fill up to a certain point, and that's it. And it will stop. And here's why. Because the more full it gets, the higher the pressure of the water is at the bottom. And more of it goes through the drain because of the pressure. So it stabilizes, you have one level. Okay, now increase the level of water coming in, it'll go up a little bit higher. But the pressure will go up the equivalent, and it will go out just that. It will never overflow, ever. Because you always have that pressure increase. So why is this important? Because I want you to visualize the water in this tub as being the reverberant field, and the spigot being the speaker. It's putting energy into the tub, and at some point it stabilizes. And that's all dependent on how much absorption you have in the room. That's what the drain is the absorption. Okay. Now, I'm going to take you as a person, and I'm going to ask you to lay down or just sit down in the tub. Okay. Now, as long as your head is above the water, you're breathing just great. Right? Now, as you slide down in the tub like this and get farther back, you eventually slide down to the point where your nose is still out of the water, but the rest of your head's underwater. Are you breathing? As long as your nose is out of water, you're breathing, right? Okay. Now I'm going to imagine, let's go down another 2 or 3 inches. Okay. Or 4 inches, depending on how big your nose is. At some point, your nose can go underwater. Now, it could be 1 inch underwater. It could be 2 feet underwater. You're still breathing water. True? Are you equally dead? Guess what? That is the reverberant field in a room. Okay, your ears are in the reverberant field. It's underwater. All you'll hear is the water. That's what I mean by the reverberant field. So that's why it looks even no matter where you check it, is because it is even. Because there's no longer speakers adding to it. It's only the room that's doing it. And the room has a certain amount of absorption. Okay. That's how absorption works. So if you get beyond a certain point, then you're not hearing the speakers anymore. You're not hearing anybody talking. You're hearing the room talking, period. That's reverberant field. So when we increase this low frequency stuff, what happens here is the sound goes through the panel, hits the wall behind it, and reflects. And it going through, it hits that wall back here. And when you're near a wall, you have two different types of energy. You have kinetic velocity energy, and you have potential energy or pressure, right? Those are the only two kinds of energy there are. Okay. As you get close to a wall, all sound converts to pressure, period. I mean, it can't go anywhere. It's going to hit that wall and stop, right? And it's going to bounce back. Well, as it gets closer to the wall, it's going to increase pressure until it reaches maximum pressure when it hits that wall. And then that pressure is going to cause it to go the other direction. So if it goes through the material and hits that wall, you're going to have maximum pressure in the back, which is a lot of air pressure. And it's confined in that 1 inch area. And because it's 1 inch, it can only escape through the outside edges. And what happens is the pressure is greater than the outside pressure is up to 1 inch. Therefore, with more pressure, you'll absorb low frequencies and you'll have increased low frequency absorption. When you reach 1 inch, the area that's available for the escape of the pressure is more than the pressure is. And therefore the sound will go, it'll increase the pressure and escape from the sides over 1 inch to the point where there's no more pressure. Therefore, there's no absorption. That's why you don't get an increase in low frequencies. Okay. Now, that is one function. That's either A or B mounting, where you have it off in the air. If you put wooden panels all the way around it, seal it to the wall, now you have an air chamber inside that's being pressurized, and it has no place to go. So you're now going to have a piston. Remember, we talked about the piston effect? Okay. Same thing's going to happen. It's going to go in there and it's going to increase that pressure, and that pressure is going to stay and get big, and it's going to get bigger and bigger. So the bigger the chamber is, the more absorption you're going to have and the lower frequency is, because it's confined, just like a piston is. That's how. So if you want a panel that works on a wall, confine the edges and seal it to the wall. And then you can take it 6 inches off the wall if you want to and get an increase in low frequency. But don't just try to lift it off and have, quote, an airspace. The airspace has nothing to do with it. It has to do with the confining of the stuff, of the air. That's what makes the difference. We already talked about this. This is not true at all. Ratio of perimeter length to area spacing. Okay. I'm going to try to get this in real fast. Remember we talked about speakers? Okay, this rig you're looking at here is what I told you earlier. There's 19 microphones here poking out. And we're looking at a diffuser. And we're bombarding the diffuser with sound. And we're now getting the reflections of it, the first order reflections, just like a speaker does. So we rotate it and we bombard it, and then we process the data by taking a window, an electronic window, and excluding all the direct sound, because the sound from here will get to all these microphones long before it gets to this. So you're going to see all these different pulses show up at different times. You're going to see this hedgehog going down like this, and you just sit there and just take a window and erase it. It doesn't exist anymore. And then we're going to isolate it to the reflection only. Standards, we talked about this method of scattering. Okay, there's other problems with it, but the main problem is you're only looking at the average roughness. It's number one. Number two, the way this works is you subtract one phase from another phase to another phase to another phase, and whatever's left is scattering. One thing these people didn't bother to take into account when they invented this thing, and people here are pretty smart, but they just, I hate to say it, but there's tunnel vision a lot of times. People get so tunneled into what they're doing, they forget about the rest of the world. And I hate to tell you, but physics doesn't care whether you're sound, light, fluid, or whatever. It's the same physics. So a lot of things that occur to the rest of the world, to these people, for some reason, disappears because we're in sound. Okay, as if sound is a science all of its own. It's not. It's physics. So what we're doing here is we're trying to cram a 4D world into a 2D box for 3D acousticians. They want to see things certain ways. You know, okay, I hate to say it, I'm going to insult architects. That's what we do in our business anyway. Okay. Architects do not like to have all this science. They want to have a number, an NRC. Anybody familiar with NRC for absorption? It's an average number between 125 and 4K averaged together and divided by the number of bands. Okay, tells you how efficient this absorber is, which is ridiculous because unless you know what the spectrum is, you have no idea what it's absorbing. So, you know, but it's designed for architects so they can say, this material is better than that material. This material is better than that material. Okay, it's just, you know, that's for us. So we call them 3D acoustic, 2D, they're 2D box. We're 3D people, we understand the rest of it. And the problem is diffusion is a 4-dimensional thing. It actually occurs in multiple different directions, including phase. So here we are with the pyramid. Anybody ever see these things on a wall? Sticks out about 2 or 3 feet. Okay. The idea is sound hits it, it reflects off of this, and this, and you end up with this other stuff. If you look at it in a scattering quote function, it just gives you kind of a curve that you look at and you go, oh, well, okay, that looks like, I have no idea what it means, just a curve. Okay, it's a mathematical curve, another graph. Okay, and to be honest with you, it doesn't mean crap. Okay, because this is what it should look like. This method we're inventing here to do this gives us the same thing that a speaker would. This is the reflection, the balloon of that pyramid. Now, when you see this, this is what you expect to see. Okay. When you go show this to the average acoustician, this is what they want to see. They're used to seeing horizontal and vertical polars. That's it. Nothing happens in between. Did you know that? Okay. So here you are. This is the vertical polar right here. And here's the horizontal polar here. So everything in between didn't happen, because we're supposed to give you only this. So my question to you is, you're looking at this right now. Isn't there a lot of information in between the 90-degree points? All this stuff out here and all this stuff in between here and stuff, that's all information that we need to have. Okay, that's why balloons are much more explanatory about what you're looking at than a horizontal and vertical polar. So this is what you put into your simulation program, like to do a speaker, and it will tell you what the reflection pattern of that wall is when you hit it with sound. Oh, I forgot to tell you. Let me go back. It's a little harder to see the attenuation. Okay, when you look at the color, you can see that if it's white, there is no attenuation. Okay, the energy coming off is just about the same level as it went in, which is kind of nice. That's called a specular reflection. Okay, but you notice as it goes out and goes back in off the angle, it turns red and then turns green. Well, if you look over there, you can see the green is 20 dB down. That's 100 times quieter at that point in time. Are you going to hear it? Okay, I will say this in our industry's favor. We can measure almost anything. The real question is, do you care? If you can't hear it, we may measure it, but if you can't hear it, does it make any difference? That's my point. If you're designing facilities and you're in a room like a church or something, and the sound is down 20 dB, do you care? Does it make any difference to you? You have to start to know, as a designer and a person involved in our industry, you know, what is usable information. Just because you have information doesn't mean it's good. It's, I'm trying to think, when I, and please understand, I'm older, okay? So as an old guy, I remember when we only had 3 channels of TV. Okay, it's ABC, NBC, and CBS. That was it. Okay, and when you wanted the news, it came on at 6 p.m. every night, and it was on until 6:30 every night on all 3 channels. That was the total amount of news you got for the entire day. Which means if anything happened, you had to wait till 6 p.m. to find out. So if they had an atomic war and it went off at noon, you would not know it until 6 p.m. when the news came on. In spite of the fact the whole place may be gone. Okay. My point was we lived in a much simpler world than we do today. Now when you have CNN, you have all the social media and stuff like that, you're in a world you're being bathed with tons upon tons upon tons upon tons of information. Now, how much of it is really usable to you? Okay, that's my point. So does that cause your stress level to go up? Yes, it does. Okay, in our day, we didn't have those kind of stress levels. Okay, our stress level consisted of the argument we had with our wives or our husbands. Okay, that was our stress level. Today, it's like, oh, what's going to happen with the presidency? It doesn't matter in most cases to us. We got to live with whatever there is. And can you change it by every day bitching about it? Okay, no. You're going to have to live with it. You're going to have to run your businesses. You're going to have to pay your taxes and everything else. You know, so it's called simplify your life. This is simplification in acoustics. Okay. Measuring system for speakers. Okay, there's our diffuser. You know, the conclusion is that all these simulation programs like AES, by the way, you heard him say that I worked on AES, right? Okay, I will say the same thing to you about AES as I do Odeon or CAD Acoustic or anybody else. The programs are only as good as the databases are. Anybody ever heard something called GIGO? Remember that? Yes. See, I just noticed it. The older people knew what that meant. Younger people don't. And here's why. We grew up inventing computers. Okay. Computers were invented by us, not you guys. And I always get young people. By the way, my daughter is 54 years old. Okay, that's my daughter. My grandchild is 28 years old. Okay. They all tell me we don't understand technology because we can't play with all the little insignias on the phone and stuff like that. I'm sorry, people. We invented the technology. We know what it's worth, but we don't need to do it again. Okay. And that's the whole point, because as a computer person, and I programmed computers way back when it was ones and zeros, period. There was no program languages or anything, just strictly binary. What we learned was if you put garbage into it, the computer is stupid. It will put out a bunch of garbage too. Okay. Anybody ever know that a turkey is a stupid animal? You know how stupid they are? Don't know this either, huh? You got to get on a farm once in a while. Okay. Turkeys will drown in the rain. Did you know that? Did you ever notice that when you graze turkeys, they're always in a building that's covering them? It's because when it rains, it falls on their heads and they don't know any better. So they look up and they open up their mouths. And when they do, they drown. That's how stupid they are. Computers are stupider than turkeys. Okay. You give it information, it will go, oh, that's good information. I'll just spit it right back out. You know, I got people telling me all about how AI is going to do good things. I'm looking at it going, it's stupider than the turkey is. It's only going to put back out what's gone in. How many of you believe in Wikipedia? How much of Wikipedia do you believe? If you go and ask about acoustics, okay, 99% of what you get will be bullshit. Okay, that's a simple fact. If you go on YouTube and look at all these different videos about how things work, okay, we got guys out there saying, oh, I can measure the low frequency of this material because I have a mattress in my room and I can tell you how much absorption that mattress does because I put it in my room and I measured it before and after. Well, but you don't know what else is going on in the room. Okay, it's still your bedroom. It's not a reverberant field. It's not a diffuse field. You can't tell. But they'll say, oh yeah, it absorbs this much. No, it doesn't. You put it in a real room and you'll find out it doesn't do anything like you said it does. Okay, but this is the kind of stuff that's out there and people read it and look at it all day long on YouTube and say, I understand all about sound because I have a good stereo system. because they have a good stereo system. They're acousticians. And I'm sitting here going, okay, sorry guys, if you design systems, I was there, I've done that. I know what you are doing through, but it took me a long time to figure out that I have more of an effect on a sound system with my room than you have on the room with your sound system. Okay, I can take any good speaker, put it in a crappy room, and it'll sound crappy. I can take a really cheap system, like the old days Radio Shack system, and I can put it in a really good room, and it will sound great. And that's all because the room sounds great. And this means you need to learn more about acoustics. The more you know about acoustics, when I was a kid, I was told I had to learn a whole bunch of things that I didn't want to learn. And why? My mom told me, my dad told me, self-defense. Okay. How many of you know anything about cars? Not much, right? Okay. Learn about cars, because the average mechanic will try to cheat you if you don't know. Because they're human, people. They're human. Humans are miserable people. Okay, as a general rule, if they can get away with something and they will cheat you for it, they will do it. Okay, because they're in competition with you. Okay, so you need to learn certain amounts about cars, certain amounts about sound, certain amounts about counting, all kinds of things in order to keep from people from messing around with you. You don't have to be expert in anything. Okay, experts are a dime a dozen. Okay, but people who are generally educated are not so easy to find, because they're reasonably smart in every area. Spend some time doing that. We're doing one area here in acoustics and sound, and there's other areas besides. I want to finish up a couple things here for you, okay? I'm going to show you some information that I just measured this week. Okay, familiar with FR 706? We talked about fiberglass pads, panels. This one is 4 inches thick. If you look at the standard data available from Owens Corning or anybody else, it's from 125 hertz to 4K. That's the standard that C423 allows. If you restrict it from here to here, that's what you get. And everybody says, well, it doesn't do anything at low frequencies. Well, 125 hertz, how do you know? It stops at 125 hertz. Okay, because nobody else can measure it below 125 hertz, not even close. Okay, the average laboratory can measure at 250 hertz, that's it. Anything lower than that, you're below the Schroeder cutoff size of the room. Therefore, they're making guesses, anything below that. So the size of the room determines how low you can measure. We all know that. It's acoustics. It's a longer wavelength. It doesn't fit in a small room. Okay, this is why I get a kick out of people saying, I have 20 hertz in my car. And I'm kind of going, okay. Or I have a stereo system that has 2,000 watts of power. And I'm looking at it going, okay, electronically. Did you look at the specification? Well, yeah, it says 2,000 watts. What does it say besides that? Peak to peak. Oh, okay, well, that's automatically 1,000 watts peak, and times 0.7, that's 700 watts. So now you're down to 700 watts from 2,000 watts. That's a big difference in power. And that's still the same power. Okay, that's about the power you're going to listen to. It's the same way here too. If you can't measure in these areas, then you can't report it. Okay, the accuracy goes down dramatically. The accuracy of the average laboratory out there at 100 hertz is about 20%. Not very good. Okay, we're able to measure all the way down to 20 hertz. It's the same level everybody does 250. What does this show you? Very, very even absorption across the entire range of frequencies, going all the way down to 80 hertz. Now, how many people would love to be able to trap 80 hertz in their listening room or their recording room or in any room they're in? because that's a frequency that causes some major problems. Nobody knows this can do it. So all of a sudden, we just rejuvenated 706 as being a good material for treating a room, because we know it goes all the way down to 80 hertz. Nobody else knew that before. Okay. So this is, by the way, this is 4 inches of it. So you would expect the 6 inches would do better, right?
There's a question on the chat in Zoom.
Oh, okay, great.
Why is the frequency range 20 hertz to 10K only? Why not up to 20K?
It could be, but nobody, is there any sound that you're worried about dealing with, especially voice, above 10K? Secondarily, almost all of the programs that are used for predicting sound stop at 10K. That's the main reason.
Okay, thank you.
Yeah, could it be 20K? Sure. I mean, it would take us about 3 seconds to change our reporting, because it's the same information. All we do is just process it differently. I hope that answered the question. Okay. So here we are, 6 inches, supposed to be better, right? You notice it's not as even. Okay. Sometimes additional absorption is not necessarily usable because it affects other things. So if you have this uneven response, your room may not be as even as you would like it to be. So in essence, 6 inches is not better than 4 inches. It's just different. Okay. Now, if you could use this extra at 80 hertz, and this extra a little bit at 500 hertz, that's great. Then you use this material, but you need to measure your room before you try to put material into it to figure out what you need to compensate for it. Now, anybody familiar with something called PET? PET is polyester. What else is made from polyester? Water bottle, Coke bottles. Okay, it's all recyclable plastic. This is polyester. So here you have a material right here that is recycled bottles converted into a mat that in most cases is used as a topper for your mattress. So you buy these toppers that are not foam, they're polyester. And guess where they're made? They're made in Elma, Washington. Elma has the largest manufacturer of PET in the world. And here's this little town of 7,000 people, and there's a building hiding in the woods you can't even see that is the size of 5 football fields with machinery making PET day and night for people like Joann's and Posturepedic and you name it. And it's like, I work in Elma. I didn't even know it was there after 13 years. So I ran across it by accident. And we went down there and we got some material because it comes in little mats and it's very nice and it's recyclable and you can recycle it over and over and it's nice and environmentally good. So I measured it. Here is 4-inch thick PET. It's not as good as OC for the overall, but look what it does here at 40 hertz. This peak is almost perfect absorption, almost 1.0, 100%, right? My point to you is, this is 4 inches. It's sucking out sound like crazy at 40 hertz. This is stuff that people said couldn't be done. So now my question is, why can it do it? Well, here's why. Okay, again, we get to physics. Okay. Owens Corning is fiberglass strands held together with an adhesive. You pour some kind of a glue into it, and then it puts it all together, and you make mats of it. You just kind of put it together and layer it down, and it solidifies and becomes these little blocks or these pads. This stuff is like cotton. You comb it like a cotton gin. You comb until you have strands. And then you make these little layers of it. You keep laying down layers upon layers upon layers upon layers upon layers. And you end up with something that's about 20 inches thick when you're all finished. And then you run it through a machine that has rollers and heaters. And it rolls it down to 2 or 3 inches thick. And it heats it up and it melts some of the polyester, which is what happens to bottles when you melt them. And it holds it together. Now, here's what happens. On the outside, you have a hard surface, which is very reflective. Okay. And as it goes through, it gets more and more dense as it goes to the center because of the liquid inside when it melts. So instead of having a consistent resistance to sound, it has a variable. So it's less resistance on the outside, and as it gets to the center, it gets more resistant. And as it gets more resistant, what does it do? It acts like a diaphragm. So the center is like this thin little layer of glue that does this inside of it. And diaphragms at 40 hertz. Nobody ever knew that occurred. We discovered this just a couple weeks ago, and all of a sudden, you have a new material here that is going to take our industry by storm. Because there's a million people that want that low frequency absorption. And all you got to do to cover the high frequency is put a board on it with little holes drilled in it. So it reflects the high frequencies and allows only the low frequencies to go through. And now you have a low frequency absorber that'll suck the guts out of the room. Okay, this is something we didn't know. So we assumed 4 inches thick. Well, I hate to tell you, I measured 1 inch thick too. It does exactly the same thing. 1 inch thick. And on top of that, here is 6 inches thick. It has higher frequency, but look now, the low frequency is now 31 hertz to 40 hertz. This is sucking out frequencies that people never even thought could be done. And look at the thing, 0.8 absorption coefficient. This is a very efficient absorber at that low frequency. And yet this stuff, instead of having these massive units to suck up low frequencies that cost $1.5 million, this stuff is right around $3.50 a square foot, which means you can make nice panels and put them on the wall, separate them, and all the rest of the stuff. And you can suck out the low frequencies out of your rooms, which now gets rid of all the boominess. This is one thing we discovered.
Ron, how much does a square foot of that weigh?
About it's weighed in cubic feet.
Okay.
About 3.5 pounds.
And is Joanne Fabrics going to have that?
Oh yes. But they have the 1 inch stuff. They don't have the thick stuff. That you have to get that from people like Sealy or Posturepedic or somebody else like that, because they're the ones that have it made. Now I will tell you this: the guy who paid for these tests is a designer of studios in Jakarta, Indonesia. He's an American, and he designs recording studios. Has for 20 or 30 years. His name is John Brandt. Anybody ever familiar with that name? Okay, he's going to be making these panels and selling them. He spent the money to do this. This guy, you have to understand, he is a consultant, just like the rest of us are. But he just got finished spending $40,000 for testing for the last week and a half for materials that the average people never test, because who's going to pay for those tests? There's no market for it. Well, he decided he was going to. So he's going to profit from it. Okay? Because these are his tests. Nobody else has these tests. You've just seen the result, but you don't have the tests. You don't have all the numbers. All you see is the graph. That's all there is. Okay? So be aware that this stuff will become available probably in the next month and a half to 2 months, available for purchase in panels. And it probably will be no more than probably $100 a panel. Somewhere that region, including framing. They'll all be framed in mahogany or Douglas fir or something. Don't know. I'm not having anything to do with the building of it. I'm just telling you what's probably going to happen. It'll be covered with nice material and stuff. It'll look nice, just like the panels regularly do.
Are you
So-
going to have his contact info on your website?
Actually, he's probably on the Zoom. I gave him the thing. He's probably watching in on Zoom from
On this
Jakarta.
here.
Huh?
He's with us today.
Yes. He's in here listening, and also the next one I'm going to show
Yes, he
you.
is.
Yeah, the next one I'm going to show you is Richard Lenz. He has a company called Real Acoustics, and he designs scattering, scattering materials and diffusion. But he also is the leading designer of low frequency absorbers right now. And he was just here 5 days ago, 4 days ago, something like that. I forget, within the last. He should also be with us on our Zoom as well. I invited him as well.
John posted in the chat that PET is naturally fire resistant. We have done fire rating on these materials.
Yes, they're all A-rated.
Cool. John, if you want to post your contact info in the chat, that would be fine.
I told you, when I knew I was coming up, I invited these people that I see around the rest of the world because of this stuff. Okay. So I just want you to see something here. This is a diaphragmatic absorber. It's 32 inches wide by 48 inches high. It's 8 inches deep. Okay. And it goes in a room for low frequency absorption. Now, there is no standard anywhere in the world for measuring low frequency diaphragmatic absorbers. It doesn't exist. You cannot use C423 because that is designed for porous absorbers where velocity goes in and gets slowed down. Low frequency is a pressure absorber. Therefore, it only works when it's against the surface. Okay, so here we are in this test. This is done the way, quote, traditional has been done for years. If you're treating low frequencies, what do? You put some kind of absorber in the corner, right? Wrong. This is something that we discovered last week. Wrong. Not where you want to put it. And here's why. You get trapped air in the corner that resonates on top of the absorber. So what do you have here? You have right there the resonance of the air cavity behind the absorber, which may or may not be predictable. And then you have the absorber somewhere in this area. Okay. Now, if you notice this absorption coefficient 1.4, that's a pretty thing. But the point is, it doesn't exist. It's the air behind the absorber. Okay. And that's trapped because, and by the way, it's not trapped because it's trapped behind the whole thing. It's open to the rest of the room. It's just resonating because of the size of the trapped airspace. Okay. So here we measured this one material. Okay. And we talked about it for quite a while and thought, well, that's really weird. Why do we have two posts here? And, maybe it has to do with how we're testing it. Again, there's no standard for doing this. Nobody has measured below 100 hertz. So why would people have a standard for it? Well, it's because we're now coming up with things we have to measure. So we then measured it by laying it down on the floor against the wall. So one edge is against the wall and the rest of it's on the floor. And just, different around the edge, the perimeter of the room. That's what we got. Look at the absorption coefficient. Anybody read it? Come on, guys. It's participation. It's not a painting out there.
Too small.
It's 3. It's an absorption coefficient of 3. When's the last time you heard of anything exceeding 1? Okay. I mean, this is like, okay, is that real? Even me who believes in things above 1 goes, 3, no, there's something wrong here. And it has to do with the fact that this thing is up against the wall and you have a pressure point bouncing back into the thing. So you have the floor is a pressure point and the wall is a pressure point, and they're combining and causing weird things going on between these 2 points. So then we took them and we stood them up against the wall. Okay. Like it would be used in real life. If you put these in a recording studio or whatever, you put them against the wall. That's normal. I'm sorry, I was wrong. The next test is we put them on the floor, just like the standard C423 test, like we test everything else. And that's what we saw. Not very much. It's about 1.0, and it's about somewhere between around 80 hertz, 63 hertz in that range. Okay, this is what it does when it's in a position where you don't have pressure and all you have is velocity. It grazes and it doesn't work very well. So this is what you would get if you measured it according to standard C423. Now, theoretically, it should do a lot more than that at a different frequency. So this is why we don't think this is correct. So then we put it against the wall and we space them apart. Now, why space them apart? Because when they get them too close together, they start interacting and doing weird things also. So everybody says, well, I'm going to buy 3 of these and I'm going to put them together into a group of 2 plus 2 and put them on a spot in the wall. You don't want to do that because it does weird things, low frequency, long wavelengths. It's hard to predict what it's going to do. When you measure it, it comes up with all kinds of weird things. But if you take them and put them against the wall and space them at least 4 feet apart. Remember we talk about that absorption thing with spacing? You got to make sure it's beyond that 4 foot. You space them within 4 feet apart, you end up with this. And these are consistent and they match almost completely what the predictions are. That's what that little unit does. 32 by 48, and it sucks out the sound like crazy between 63 and 80, 1.8, 1.7. This is 3 to 4 times to 10 times more absorption than you normally would get. Now, if you want something that's usable, look at 0.8. Okay, look at 0.8 down here, right here. The frequency range you can treat is between 38 hertz and 128 hertz. You can treat that whole width at one shot with this one piece of equipment. And it works really good. It sucks out the bass out of a room like you know. I don't know. What can I say? I can't. Okay. The point is, it will suck out that low frequency. Okay. And this is just one unit. Okay. I just got finished testing about 7 or 8 units, different sizes, and they all have different frequency ranges. This is the smallest of the units. It has the highest frequency range. Okay. I can tell you, and I can't show you the data on it yet because believe it or not, the guy who paid for this and is making this just got back to his office a couple days ago from our place because he was up here for a whole week measuring. Okay, so you're talking about having the latest data. Nobody in the world has this data except him. And you guys now have seen your graph. Still don't have all the other charts and stuff, and the reports are not official yet, but they will be when I write them up. Okay, but he should be here in our Zoom as well, as Richard Lenz. And I can only tell you that this guy is farther in advance than anybody else in the world in low frequency treatment. And he has some bigger ones that are like 4x4 or 4x8 that go down as low as 30 and 35 hertz. Okay, so if you're trying to treat things like churches or rooms that you're trying to get rid of that low frequency rumble, all you need is 1 or 2 of these things in a room, period. They run roughly, I think his comment to me was somewhere in the range of $600 to $800. Yeah, they weigh, they weigh 50 or 60 pounds a piece, but what can I say? They're big. They're like, say, 32 inches by 48, and they're 8 inches deep. They're like a box. Okay. So I just wanted you guys to know, and I wanted to kind of go over that with you. Remember I told you about I'm going to update everything to the latest. Well, you guys are updated to within 24 hours of the last measurements. I don't think I can get you any more updated because I didn't measure today. Okay, but I did measure yesterday, and that's what you have here. Okay, so is there any questions on stuff you've heard so far? I mean, I haven't heard a question except that one question come through. I'm just shocked and it's like, whoa, usually I get peppered with questions. So I'm here if you want to. Otherwise, I am done. Anything?
Wow. Does anybody have any general acoustics questions?
Yes, anything.
For Ron? And feel free to unmute yourself.
Yeah, we got plenty of time. If I don't fall on my chair first.
Can you talk about why the scattering coefficient is a function of absorption?
Yeah. Scattering has always been based upon what we call independent unevenness of surface, and that causes different phases and stuff. In reality, the edge effect is also based upon the the phase. I don't have it here in front of me, but I can show you what happens in a diffuser in the phase balloon. Up till now, nobody's ever studied the phase balloon of a diffuser. And what we find, and maybe I can cover this real fast if you don't mind. Are you familiar with the BAD panel?
Yeah, from RPG.
Yeah, okay, good.
Could you explain it anyway, please?
Yes, I'm going to right now. The BAD panel. When we first measured it using scattering back 10 years ago when it first came out, we used the 17497 to measure it, and we basically came up with nothing. It was a reflection of the spectral reflector. There was nothing that showed up at all. Okay, and we measured it using the 17497, and there was nothing to report. We brought the same units up to our new unit, and we measured them using the new method we have with the reflection. And if you look at it, the reflection patterns are exactly the same as a spectral reflection. So all you see is whatever angle it comes in goes out at the same angle. There's no diffusion at all. But what it does do is we noticed something in our speaker lab thing where we're able to look at the phase balloon of the same thing. And as it went up in frequency and went up in frequency, all of a sudden it exploded. In the phase balloon on speaker lab, if you have something that's coherent, and you see all these reflections coming out the same way, it forms what we call a flower petal, like a rose. If you look at a rose going in, you see these flower petals going around. Everywhere you see a petal, all those phases are coherent in the same phase. Okay, so the idea here behind diffusion is to randomize that as much as possible. And what we noticed is from 12K up in a BAD panel, the phase went from a spectral function to a completely random function that looked like a sea urchin. And every time it makes a spike, it goes through 360 degrees of phase change. So we have phase changes as high as 2,000-3,000 degrees. Okay. I opined, okay, that this may be something that your mind doesn't perceive that way. It goes, oh, okay, maybe the phase change is something your ear hears differently. Well, one day I was leading a tour of the APL Applied Physics Lab up at University of Washington. And University of Washington is very well known for bioacoustics. There's a whole bunch of different areas of acoustics, and also underwater acoustics. That's their two specialties. Bioacoustics is how does the ear hear and how does the brain perceive it. I was doing this tour and I mentioned this, that I saw these phase changes, and what would happen is you'd have one set of phases hitting this ear and one on this other ear happening, and it would sound bigger. And I had listened to these bad panels myself. I have rooms that are solid concrete, and I go in and listen to them. You could hear all the reflections coming off. You put the BAD panels up, and the room just sounded bigger. Okay, that was a subjective thing. I went in and said, "Oh, yeah, that sounds better." Don't know why, but it does. When I mentioned this to the APL people, this one young lady who was in class said, "Well, of course, we've known that for 25 years." And I'm going, "What did you know?" And she says, "In bioacoustics, your brain interprets change of phase between two ears as space. That's something that happens inside the brain." Little did I know, I'm architectural acoustics. And she's telling me, "Yeah, we've known that for years." And I'm kind of going, "Well, we didn't know it." And she says, "That's because you don't understand bioacoustics." And so that determined when I listened to that, it's like, well, okay. So then I tried to figure out how to describe it to somebody like you guys. And it's very easy. How many of you have played guitar? Anybody play with an amplifier? Familiar with Fender amplifiers? Okay, there's a control on the Fender amps called presence. Everybody know that? You know what it does electronically? Because I'm an electronics engineer as well. Okay. When you turn up that thing, it increases the high frequency. It actually injects 16K noise into the sound. Okay. And it makes the sound more spacious, like an echo, like a reverberation. Okay. And that's because your ear hears that 16K various random stuff and goes, "Ooh, it sounds more spacious." Anybody familiar with Mackie? Everybody up here should be, right? Okay, their mixers have a control that nobody else has. It's called air. You ever seen that? What does it do? It injects 16K noise into the channel. It gives you a more spacious sound. This is because your ear interprets it as more space. This occurs when you're in a cathedral in Europe and you have the high frequencies bouncing around everywhere and you have scattering, okay? And your ear goes, ooh, difference in phase response, okay? It sounds like more space. Okay, the reason the scattering testing does not work is very, very simple. In a reverberation room is defined as a room with no discernible mixing levels of magnitude and no discernible phase differential. Understand what I just said? There's no definable mixing of magnitude or of phase, because that's what diffuse fields are. They don't have those things. Okay, so when they first came up with scattering, they measured them in a free field, and you can measure an impulse response from an angle and get an answer and get a phase. Then you rotate the material 5 degrees, do it again, and you do it over and over, and you take and add these together, and what falls out at the end is if they're specular reflections, they add. And if they're random reflections, they cancel each other out. Sorry. Okay. So what's after all the cancellations, whatever energy that goes between the specular and the total energy is called scattered energy. Okay. That works great in a free field. But when they wrote the standard, somebody out there decided that if you're going to cancel out all that energy, we should be able to measure that in the reverberation in the room being canceled out. So the idea was you're supposed to go into a reverb room and measure the phase change between this measurement and that measurement. Well, I'm sorry, but in a fully diffused room, there is no phase change. You can't measure it. And that's what we discovered. We had the only facility in the world that could measure full scale in California, but we were in a 200 cubic meter room and it was not fully diffused. And we got measurements. We believed in it. We even brought the turntable up with this 12-foot in diameter. I have all the samples. When I brought the samples with me in the turntable, we installed it in our new room, which is 800 cubic meters, and it's much more diffuse. And all of a sudden, we started measuring the same thing, and we could never get back to that answer. In fact, we came up with completely random answers every time we measured. So you measure it one time, you have one set of answers, measure it the second time, a different set, and it's completely random. You could never duplicate the measurement under any conditions. And that's because the room doesn't have measurable phase differences. And that's why 17497 doesn't work. You can do it in, I think D'Antonio does it in, I think it's percentage size, 20% sample size, because they do it in a miniature room and they do it in a room, a reverb room that's 20% smaller, et cetera, or 80% smaller, et cetera. But the point is, his room that he's measuring in is not diffuse. So therefore you can measure, but that's the standard calls for a diffuse room. So if it calls for a diffuse room and you can't measure it in a diffuse room, then at that point in time, the standard doesn't work. Therefore, it needs to be gotten rid of because it's not scientifically be able to be used. And that's why. I hope that answered, that's a long answer for that question.
Ron, back to that 16K noise.
Yes.
Is that some kind of noise generator in there, or is it simply an EQ that's amplifying?
No, it's just a noise generator. If you look inside all these circuits, you're going to find there's usually a transistor or a tube that is basically randomizing just white noise is all it is.
Huh.
And it just gets piped in by the dial. That's all it does.
Crazy.
I was shocked when I found that out. It was like, oh boy, talk about feeling stupid. I repaired those things for 40 years and never knew what it was. I just knew that it worked. And then when they told me, it was like, I mean, I actually felt very stupid when that student told me, well, we've known that for 25 or 30 years. And I'm kind of going, how come you guys didn't tell us? Well, you don't go to those meetings. We do. And what it proved to me is people in aero acoustics and planes know things that we don't know. People in sonar and underwater acoustics know things we don't know. Although, let me explain one thing to you that I get grief on all the time. Anybody know what an anechoic chamber is?
Yes.
Define an anechoic chamber for me, please.
Without echoes.
Room without echoes.
Thank you. That's the first time I've had that answer. Usually it's a quiet room. It has no noise. You go inside and you can hear your heart beating. Okay. Just because it has no echoes doesn't mean it can't have a reverb field. Reverb field is energy that is random. It can't be echoed because in echo, you have to have a mean path to get there. Okay. Everybody understand how the wedges work? Everybody says, well, they're soft, they're fiberglass. They could be, but I've seen anechoic chambers that are made with stainless steel wedges. Now, do you think they're going to absorb sound? No, because they're made for sonar underwater. Wedges would get very wet if they're underwater, if they're made out of fiberglass. They're made out of stainless steel. So when you shoot a sonar, you don't get a reflection. Why don't you get a reflection? It's because the shape of the wedges, not because of what they're made of. So here's what happens. If you have a wedge and you have another wedge next to it, okay? The angle of the wedge has to be in excess of 60 degrees. So when you go between the two, you have to have a very tight wedge. It can't be 45 degrees or anything less than 45 degrees. It has to be something very tight like this. So if you have this one and you have one next to it exactly the same, the sound coming in will hit it at an angle. It will come off based on Snell's law, it's the same old, right? Coming out. And when it comes out, it's going to go right to the next wedge. The next wedge is going to have the same angle. It's going to come back out and go back into the back of the wedge. And because of the angles between them, it's going to bounce back and forth in that hole between the two wedges until it dies. No echo. No reflection. And it's not a room without echoes. It's a room without reflections. That's what it actually means. And it's a different thing. Okay. But that's because of the shape of the wedges. So you can have steel wedges, you can have wooden wedges, you can have mineral wedges, you can have all kinds of things. But all that happens is sound will go from one reflection to the next reflection, the next reflection, the next reflection, and keep going backwards until it runs out of energy. Now, if you have a stainless steel wedge, it may take 2 or 3 or 4 seconds for it to get rid of the energy, but you still won't have a reflection. It just takes it longer for the energy to go. If you have a soft wedge, it'll suck up some of the sound and make the energy go away, but it's still the same thing. It still has no reflections. This is the same thing with things like scattering. Okay. Scattering has limitations. Scattering says you can't measure scattering if the vertical displacement of the surface is more than 1/16 of the size of the sample. So it's only supposed to be used for random patterns. Like, let's say you take a concrete block and you split it, and you take a hammer to it, and it gives you that rough, you see these surfaces with these concrete blocks? Okay, it kind of wiggle around about 1 or 2 inches or so, and you make a wall like that. That's a scattering surface. It can be explained by diffraction as well, okay? And by the way, scattering is diffraction. It just is random diffraction rather than controlled. How many are familiar with QRDs, diffusers, RPG? You see these little diffusers that have slats, vertical slats? Those are QRDs, quadratic residue, okay? Anybody know how they work? I showed you a picture of one with the reflection pattern, okay? What makes them diffuse is the edges. You know, those little fins you see? The sharper those edges are, the more diffractive it is. So if you see these diffusers that are formed out of fiberglass and molded, and they have rounded edges, I'm sorry, they look nice, but they don't work. Because it's the sharp edges that work for them. That's what makes them work. Secondarily, you are aware that they are enormous absorbers. If you ever look at the absorption coefficient of a QRD, it's about 0.7 across the board. But there's nothing absorptive about them. There's nothing in it. They're all made out of wood or metal. So how do they absorb? Or we talk about resonant cavities, like a tube. Okay, I want you to think about something about how sound works. If you have a horn in a speaker, it almost always starts with a throat. And in that thread, you will have a planar wave because it just comes out and then it goes into the throat and it's restrained very narrowly and it becomes a plane wave, what we call a plane wave. And it comes out. And as soon as it comes out of the throat, it now reaches the horn. Okay. When the sound reaches this horn, the one side of it that's going along where the horn is will continue onward out, following the surface of that horn on both sides. And what you don't realize is because it's on that surface of that horn, there's friction there. So it slows down. So all the velocity along that surface slows down compared to the center. What happens if it's faster in the center and the outside? It forms a spherical wavefront. That's how it becomes spherical. Is the horn is causing it to slow down on the outside and the center is going out, and you now have a spherical source. Okay, now I want you to think about it the opposite direction. Now it's coming up to a QRD, and you have all these pockets with all these fins on them, and these pockets have different depths. Okay, when the spherical wave hits these things, it will push into the pocket in the center before it ever touches the outside edge. Just think about it. Okay, the center is curved, therefore the center will get to the air before it gets to the outside edge. Okay, it won't seal. So as the center goes into the pocket, it's a sealed pocket. It's bounded on all four sides. So as it goes in, it's going to increase the pressure of that pocket. And in doing so, the air is going to spill out on either side until the edge of that wavefront touches those walls. So the energy is going to spill out. Now, as soon as it hits that walls, it's going to start to press on the center and push back on the wave because of the pressure, and you're going to end up with a plane wave again, going into that pocket. Now you have a plane wave, and it's bounded on all four sides, and you have a surface of the plane wave coming in that has a surface as far as it's concerned, and it's going in and pressing. You now have a shock absorber, right? It's bounded on all four sides. So now you have the energy going into the pocket, and it's pressing on that space of air and compressing the air. As compressing the air, what's it doing? Converting the heat, slowing it down. What's that called? Absorption, guys. It's absorption. And then what's going to happen is it's going to hit that back wall, and it's going to reflect back out. And coming back out is now going to be out of phase. Now you have a phase differential between going in and going out, and you're going to have a cancellation from that. More absorption. Okay, that's how they work. So you get the scattering from the edges, and you get the absorption from the time delays and stuff like that. That's how these things work. Again, this is all basic physics. It's all fluid dynamics. So if you want to study something in your spare time, just get some basic, simple books on fluid dynamics and basic physics. Okay, and you'll find it explains 99% of everything you ever want to know about sound. Any other questions?
Ron, do you ever get called on to walk into a room or desire to walk into a room and characterize its acoustics? Do you clap your hands and walk around like we do, or do you do something else?
Remember, I was one of you guys. I only got where I'm at now because I decided to take my retirement income and retirement funds and make a laboratory because I'm dumb and stupid. Okay. In order to be in our industry, you have to be just slightly on the crazy side. Okay.
That's the truth.
That's a simple fact. If you ever meet anybody who's in acoustics or sound, they always are a little bit off center. Okay. You have to be, because this is an industry that doesn't pay very well. Okay. It's a horrible industry if you want to make a lot of money. We're going to be poor most of our lives, or at least, almost poor. Okay. So, why are you staying in a business where you aren't going to make a lot of money like a computer programmer? It's because we love it. And that makes us stupid. Okay. Anybody understand what the difference between stupidity and ignorance is? Ignorance can be educated. Stupidity is permanent. Because once you decided that you have a fact in your face and you don't recognize it, and it's a real fact, if you don't accept it, now you are stupid. And nobody can fix that. Okay. Now, people out there, I know a lot of people out there that are ignorant, and we try to train them the best we can. And people do accept it. John Brandt on the line is a great believer in this now, because he's seen it happen. And you know, if you're not willing to give up what you know, what you think you know, when you have the proof put in front of your face, then you have a problem, because you're going to be forever in stupid land.
Can't you be stupid and happy though? I am.
Well, yeah, nobody said that you can't be happy. You can be happy in anything. And look at a pig in mud. He's very happy, and he's stupid too. You know, but the real point here is we're here in AES and ASA and INS and all the rest to try to educate ourselves. But you have to have an open mind to be able to do that. And a lot of us have learned the same thing for 80 or 90 years. And we all think that this is what there is to science. And when somebody presents something that goes counter to what you learned, it's like, you can't say those things. Okay. I can only tell you that, you know, I'm not the most popular person in our industry. Okay. I've pissed off more people than I could ever think about, because I just decided that here is what this, you know, I told Wolfgang Honert, who designed EASE, I said, Wolfgang, be careful what you ask for, you may get it. And he said, what do you mean? I says, you never give a consultant his own laboratory, because we will test all the things we've always wondered about, and nobody would pay for it, because we we can do it ourselves. It doesn't cost us our time except time. Money, who cares? Okay. But in reality, if you have a question, we can test those things now. And when you test them, all of a sudden you go, hold it, the answers are not what I expected. I mean, when I showed them these tests with these squares and circles and stuff, and they all had these different answers, the first question came out of a guy named Gary Manch, who was the head of the WEAL laboratory in California. He said, if I hadn't been sitting here and watching this, I would never have believed this. Okay. Ken Roy, the very well-known person who just retired from Armstrong. Okay. He was there as part of that testing too. And he's a PhD in acoustics. And he told me, he says, if I hadn't been here and watched it, I would never have believed it either. But he was there and actually did the tests. And the answers came out, and he was like, okay, not exactly what I was expecting. Okay. And that's what started this whole thing. Yes.
So I have a follow-up question to that.
Sure.
Because I didn't, I don't think I got the background. So the lab you're talking about, which is your new lab, the thing that is setting it apart is simply the fact that it's like 10 times as big as any other lab?
Yeah. Yeah, that's what sets it apart. It means we can measure lower frequencies than anybody else in the world can.
And nobody thought to do this for 75 years?
Why? The standards called for no more than 125 hertz. If the requirements are only 125 hertz, you build a room that matches 125 hertz. It's cheaper. Isn't it wonderful to find out that science is driven by the almighty dollar?
Can I ask, why is the convention to show absorption in terms of a coefficient, or as you want to do it, in terms of a constant, rather than simply dB attenuation?
Because somebody in 1927 proposed it and it was accepted. That's the only answer.
And then in terms of the way that you're presenting your reports from your laboratory, is there like a conversion formula from the constant that you're showing to like dB?
There is empirical measurements showing that. I don't think anybody has sat down and thought about a conversion of going from Sabins to a dB thing. Okay, I can only tell you that in measurements that we have done with these balloons, we can normalize the basic input level. And the way we measure these things is we put a speaker up on top, and in order to be able to figure out what the diffuser is seeing, we actually replace it with a flat plane and then put a microphone on the surface of it, a ground plane, and measure it. And we can tell you what the frequency response, phase response, and everything else level is at that point. And then we can normalize it at that point, and then create an attenuation balloon that says whatever comes out of it is reduced by so many dB. And that's what you see in those balloons where you see 6 dB down and 3 dB down, etc.
Oh, I see. It's relative to like a specular reflection.
That's right.
Okay.
Yeah.
And then how relevant would a coefficient be in low frequencies, especially in small rooms where it's a modal region?
Again, the same situation. If the room is so small it cannot support a mode, then all you have is pressure. And in that situation, the pressure only applies at the boundaries. So that's why you can put these absorbers on the boundaries walls.
But in terms of the amount of absorption that you can expect, the coefficient will still be accurate?
Yeah, in this situation, what you see on the screen right now, I think it's still up there, I don't know, but it shows like a 1.8 at roughly 63 hertz, I think it is. That's going to be probably close to around 20 dB, 25 dB of loss.
Mhm.
Just based upon the fact that a 1.0 is basically 10 dB.
Okay.
Okay.
Thanks. That's very interesting.
Yeah, it's very efficient, and these things do work, and we're able to measure and put them in a room and actually figure out what the losses are in time. We can tell you what the time losses are in RT. But I can tell you right now, the C423 is going to leave a lot to be desired for this. I think based upon conversations we've had with other guys in our industry, we're probably going to have to create a whole new standard for measuring low frequency diaphragmatic absorbers.
Do you think like the current information out there by other manufacturers is inaccurate when it comes to the low frequencies? Yeah.
Yeah. I think that's probably the most interesting question I've had. We also measure transmission loss. Okay, and it has the same limits that they call for. And in the standard, you can report 125 hertz of transmission loss, which, by the way, is measured the same as the absorption is. Okay, and you can have as much as plus and minus 6 dB and still be considered accurate. Now, I have a question for you. Do you honestly think that 12 dB is an accurate measurement?
No, that's a lot of difference in energy.
Yeah, and that's my point. That's 125 hertz. So because of the size of our laboratory and because of how quiet the background noise is, we can measure 25 hertz with a half a dB differential.
For laboratories like RAL, like Riverbank, they say that they apply a compensation curve below 100 or 200 hertz or so for the low frequency measurements. So that doesn't work.
No, it's a numerical thing that says, if we look at it, you can see an average incline or a separate linear regression that you can apply to it that is approximately good, but it'll tell you this is an approximate number. It probably exceeds this. We're just not sure.
Okay.
Okay. Just so you're aware, Riverbank is the smallest of all the laboratories in the world. So its cutoff frequency in reality, by the way, ASTM defines what the cutoff frequency should be, and that is 5 overlapping modes at any one frequency in order to be able to measure it correctly. And the 5 overlapping modes at Riverbank at 250 hertz.
Okay.
Okay. So just be aware of that. Almost 90% of the laboratories in the world are between 200 and 250 cubic meters. And they all have a cutoff frequency of around 160 hertz.
Right. The cutoff frequency definition that you just gave, that's just another way of saying the Schroeder.
Yes.
Is that right?
The Schroeder is slightly different, but it has to do with how it's measured. The Schroeder is measured by the size of the room. The other one is actually defined by actually measuring and using microphones to figure out how many modes there are in each direction.
Okay, all right, thanks very much.
Anything else?
Those were good questions.
Yeah, I think it's a great question. I thank you very much for those questions. I like this. This makes life a lot easier for me.
Anybody else? Awesome.
Thank you guys for listening.
Thank
I'm
you.
sure
Russell.
it. Thank you. I had a lot of fun. Thank you.
Bravo.
Right.
All right. So people in the room, you've been sitting for a long time. Do you want to stand up or do you want to introduce yourself and then we'll get to the end of that and we'll be done? Well, that seemed to be good. What do we want to do, people in the room?
I think we should wrap it up soon. I'm starting to fade.
Yeah. You want to go up and say who you are? There's not a whole lot of you.
Yeah, let's just do it. We can do it
Let's
quick.
do that. Go ahead,
Just
Lawrence.
quick. I'm Lawrence Schwedler. I'm the program director of music and sound design here at DigiPen and an AES member and the treasurer of the PNW section. And this has been a great talk. Thank you, man. That was great.
I'm Gary Louie. I'm the secretary of the Pacific Northwest section. I'm a life AES member. And what else do I do? I'm chair of the tellers committee for the entire AES, which handles the election, which is ongoing right now.
That one seems to not be working for some reason. Sorry. Go to the other side. It's on, but it's not happening.
Hi, I'm Eric Clausen, sound designer in the area and working on a couple indie projects. I graduated from DigiPen, so thanks for having me.
Thanks for coming.
I'm Michelle Mayer. I'm a sound designer. I work at Twin Suns Corporation, and this has been fascinating. So thank you.
Thanks for coming.
Hey, I'm Cameron Sanju. I'm a sound designer at PlayStation.
Awesome. And a DigiPen graduate. Thank you very much.
And a DigiPen graduate.
Hi, I'm August McCubbin. I'm the sound lab manager here at DigiPen, and me and my team helped set up everything for this in the room today. Also a DigiPen graduate. Lawrence will scream at me otherwise.
Yeah, I'm Jonathan Larson. I am a student here at DigiPen Sound Design program. Yeah, I was part of the team that helped put this on. This is a fascinating talk. Yeah.
Hi, I'm Ben Schwedler. I'm another student at DigiPen and a member of the sound team here. I was in charge of the video switching today for the presentation. It's a lot of fun. Thank you very much.
Thanks, Ben. Turn your mic on, Ron. Turn your mic on.
All right, there we go. This is a project that I just did a design for a church right up here in North Seattle. I think it's Martyrs Catholic Church. It's a typical get together room in the afternoon. They complained bitterly about it was all concrete and everybody would make so much noise, nobody could understand anything, and nobody would enjoy staying around. So they all leave 10 minutes after the church was over because it just was too noisy. So they asked me to do something. If you notice on the right-hand wall, there's checkerboard. Also, the back wall and the rest of the rooms behind are also checkerboard. They did this because it was reasonably inexpensive. Now, what really controlled it is if you look right above on the ceiling, remember those we had those hanging things? These are what we call lapidaries, or actually in this case, bandit, which is low frequency. Again, $1.65 a square foot for the stuff. And it sucks up low frequency like nothing you've ever seen because it's right there at about 80 hertz, 90 hertz, and it's got a 1.4 absorption. And every bay in there has one of these things laying in it. and reduce the reverb time from 4.5 seconds to 1.2 seconds. And it was reasonably inexpensive, so I think it's totally $1,000 for everything. So, you know, just wanted to give you a heads up that you look, you can actually see this stuff in action. Huh?
You gotta do more design.
I used to. I did it for 12, 14 years. Anybody familiar with Benaroya?
Yeah, oh, yeah.
I designed Benaroya. Okay, or La Scala in Milan. So that's the kind of stuff I was doing. I did Las Vegas Motor Speedway and a lot of places like that. Biggest church in the world, Korea. So I've been doing this for a long time. I've been 55 years at this now. I'm an old guy. My kids are 50-some years old. So, you know, all you can say is I plan on doing Quranic. I want to still be working at 100 years old. And, you know, keep on teaching. I really am intending to teach now. I really want to teach because they tell you is I explore all this other stuff and research it, but it never goes any farther than what the books are and what you educate. If you don't pass on what you know to other people, it dies. So my job is to educate as many people as possible to pass on what I've learned over these years. And that's what my job is now at 77. I don't care about designing anymore. I've done enough of it. But I do care about the education of younger people so they can continue on. And I hope at some point to find somebody to take over my laboratory because I'm getting old. Okay, so if anybody's ever interested in taking over the laboratory, let me know. But if you are, then we talk about that. At some point I want somebody to buy a part of it, but I'm going to be willing to make some thing. So if you're interested in doing that, get a hold of any of the guys. They'll give you how to reach me or call me at the laboratory. And if you want to come down, I'll be happy to show you a tour of the place. Oh, I'm sorry, you guys are still around. Do you mind?
What's that?
I forgot to show you something.
Oh, right, we've got a video here.
It's 3 minutes long, people.
Go ahead.
Sound, let's see, where I get sound.
It's on here. There you go.
So now is the end start of our converters and eight actually for this. I mean, these are this room is so large, it's diffused anywhere inside the flat line. We have a wall in there right now that is basically an STC65. What you see here in the flat line is the limit of this room in order to be able to measure 20%. Yeah. The original thing was we were going to we have down here the convert time at 25 hertz, 37 minutes. Okay. Because every time I do a test in this place, no matter what it is, it's a minimum of 1 gigabyte to 1.5 gigabytes of data. Yeah. What you're looking at right now is a turbine building where they made the electricity. Right now, this is set up for a diffusion test. And what we're doing is we're bombarding the sound from up there, coming down, hitting it, and then we're looking at the first order reflections. I was really quite surprised, found out when we actually measured them. But yeah, it's right around 20 hertz. So we can do subs in here and everything. I watched it being built many, many years ago. And my first thought was, I need someplace inside of a mountain. I was actually going to cut into a mountain. And then I was passing by it and Bonnie said, well, have you ever thought about that place up there? Why? She said, well, it's really heavy. That's 1, 2. So I Neil Shaw, by the way. Said, yeah, they opened it up as a business park and could I look at it? Well, let's see, 20 feet of concrete should be at least as good as a hillside is for keeping it stable temperature wise. There's 150 holes in this floor that you can't, and all of them go 40 feet straight down. Now, how safe is it? Well, we've driven a forklift here, so not too worried about it too much. The person asking those questions was a guy that a lot of you know, named Neil Shaw. Been around for a long time, you know, AES stuff. And the reverberations that you heard in there, the reverberation that you heard in that area was about 8 seconds of reverb time. And when you saw when I turned my head, couldn't understand a word. Okay. So he was trying to clean it up, and the best he could do was get a little type thing. So at least it gives you an idea of how big this place is and what's there. You know, we have, and the earthworks mics. Okay, we have M30s, we have 65 of them in our test facility. You know, plus a couple of B&K 4955 real quiet noise ones. And like I said, you know, we got a lot of equipment, and you know, I'd like to be able to train somebody to do this because I can't do it forever. At some point I need to retire. I am just physically not able to. So if there's any interest in it, let me know. I'll be happy to work with you and train you and stuff like that. Okay. Thank you very much.
Thank you, Ron. Anybody else here to say who they are? Okay, let's turn it over to the online people. I'm going to stop sharing and let you folks talk amongst yourselves. There's not that many of you. Okay. Steve, where are you and what's your audio deal? Savanu.
Hi there, everybody. I am Steve Savanu. I am an AES member. I'm located in Ohio, so it's about 1:15 in the morning here. And I'm an audio engineer, primarily classical and jazz music recording. And in the summertime, I do live sound. I have a concert series every week and other events. And I am a journalist. I write for a publication called Front of House Magazine, and I do product reviews. And I just finished one that'll be running next month on the new QSC L-class line array systems. So that's my world.
Where are you in Ohio?
I am near Cleveland, Ohio, in a little town called Hudson, which is a fun little town. It's like a New England kind of looking place.
You grew up in Akron.
Yep, I am halfway between Akron and Cleveland.
Oh, I know where you're at. My cousin lives in Hudson.
Mm-hmm.
Yeah, it's a very interesting place. I spent most of my young life till I was 18 in Akron. I graduated from Bookville High School.
Okay.
So thank you.
All
I
right.
appreciate it having a young person in Ohio.
Let's go to Mark Scott. Where are you and what's your audio deal? Are you able to unmute yourself, Mark? Apparently not. Mac Perkins, where are you? What's your audio connection?
I'm on Whidbey Island, about 20 miles north of Seattle. So I've driven past that cooling tower many times, headed to various clients that I used to work for out there. Did theater lighting and sound systems for quite a number of years. A lot of live mixing, and I've been away from it for some years now, but still very interested. And I definitely learned quite a bit tonight.
Well, if you ever drive out that direction again, give me a call in advance, and I'll be happy to show you, give you a tour of it.
Yeah, I'd love to toy with the idea of, getting involved with that, but I'm the same age you are, and I'm looking for fewer things to do, not more.
Well, we'll still give you a tour of it and give you a chance to play around with it.
Yeah, no, that's having a facility to do that sort of thing in is really a dream, because I've always been curious about how things really work. And, some of the things I've heard and run across. So like, yeah, I'm not quite sure why, but I found some of the answers, but there's always things to learn.
Yes, thank you very much.
All right, thanks, Janie Wallach. Where are you? What's your audio deal?
I'm in Seattle, Washington, and I record live music. And about 3 months ago, I downsized and upgraded my gear simultaneously. And if anyone in the greater Seattle area would like to check it out and accompany me to shows, I would be happy to show it to you up close and personal. Just
right.
let me know in the chat.
Great,
Thank you.
thank you. Enrique, where are you and what's your audio deal? You've been actively commenting tonight, and that's much appreciated. Are you able to unmute and talk to us?
Okay, no video, but audio.
Hi.
I am from Mexico, exactly from Cuernavaca, Morelos. This is a 30 minutes travel from Mexico City. I am the audio industry since 1986, starting for my father. My father is an electronics technician, so that's the beginning. Now I'm a retailer salesperson. Every brand that you can imagine, I sell it. And I was happy to be here because now I know something. I don't know nothing.
Welcome to my world.
Yeah, I mean, you can read every book that you want, but if you have a laboratory like that, you can take down a lot of books.
Yep. All right, great. Thank you. Let's go to Benedict. Where are you and what's your audio story? Are you able to unmute? Benedict? Apparently not. Rod, where are you? What's your audio story?
I'm an electrical engineer registered in the state of Oregon. I do audio work as well, and do recording work. I'm a life member and in some regards retired a little more from the electrical than the audio recording at this point, but still. And part of my electrical engineering experience was working at the notorious Hanford operations in Richland, Washington, and was there about the time Washington Public Power System went belly up on it, all its nuclear programs.
Welcome.
About how the, excuse me?
I said, welcome to Samsung.
Yes, such as it goes. So, but very interesting presentation, and I see our main speaker has checked out. I did sort of have a question for him, but one of the things that I have to deal with in doing recording work in remote locations is I have to live with the acoustics I'm walking into, which are not always that good. And I'm always sort of looking for that critical point between the direct field of the sound coming from the performers and the sound coming from the rest of the room. And if I get too far back, of course, everything becomes unintelligible, and too close in, and it really doesn't have the flavor of the room. So that's been one of my little challenges with the acoustics. And
Ron is still here, so you
I'm
can.
still here.
Just.
excuse me?
Ron is still here.
Yeah.
Oh, he is.
Yes, I'm here.
Any comment about that?
Yeah,
About how you got the dead whoops place?
I watched it being built back in the 70s, and the place I was at in California was buried in a mountainside, and I couldn't find another place in a mountainside, so I figured I'd find a building that was like a mountain, and that happened to be up there. And I just called up there one day and said, "Are you guys going to do anything with it?" Because it was in mothballs for 20 some odd years. And they said, "Well, we just turned it into a business park. If you can use any of our buildings, come on up." We went up and looked at it and said, "Oh, there's a built-in mountain. We're the only people in the building. Nobody else can modify it because you got 5 foot thick concrete walls."
You got it.
Okay. Wow, yeah. Okay.
So I'm glad to hear that you were involved in the, at least because people don't understand nuclear energy, and that's too bad because it was actually okay.
Well, one of the things that was a little disturbing when I was working at Hanford was that the Department of Energy was wanting to increase the number of strategic warheads the United States had by 4,000 units. And I said, good God, they're going to have to get this thing going full blast. And the price of uranium had jumped from something like $7 a pound to $42 a pound. And I think people came up short on it. And what do we need? Power or atom bombs? And I think the atom bombs won out. But I know that in other ventures I'd been into, it was known that the United States was backlogged on the amount of enriched uranium that they had by about 5 years, and they were very busily trying to get that back to normal, but still.
Yeah, they're down to 1,500 warheads now
Yeah,
from 7,000.
you wonder.
All right.
Thank you.
Let's call it a day, everybody.
Yay.
Thank you
Okay.
so much, Ron, and
Okay.
everybody else for coming.
Thank you.